Have you ever stared up at the night sky and felt that strange, almost electric tingle of curiosity, the sense that there's so much more lurking beyond what we can see? The universe, for all its grandeur, is still hiding its deepest secrets in plain sight. What if I told you that the stars, the galaxies, even the laws of physics as we know them, might just be the surface of something far stranger? Today, we're not just skimming the cosmic surface, we're plunging into the unknown, exploring 42 unconventional approaches that shatter our everyday understanding of reality. These aren't just abstract ideas, they're keys to unlocking the universe's hidden frameworks, from the mind-bending dance of quantum particles to the eerie, unexplained whispers of distant celestial objects. Think about this for a moment. Everything we've discovered so far, from black holes to dark matter, was once considered impossible. And yet, here we are, standing on the shoulders of those breakthroughs, peering into the next layer of cosmic mystery. What if the universe operates on rules we haven't even imagined yet? What if time, space, and even causality aren't as fixed as they seem? This journey isn't just about satisfying curiosity. It's about rewiring how we see existence itself. Because when we tug at these threads, we're not just learning about the cosmos, we're uncovering the invisible scaffolding that holds it all together. So why should you care? Because these ideas don't just belong in textbooks or labs. They're alive, pulsing through the fabric of reality, waiting for someone, maybe even you, to question, to wonder, to connect the dots in ways no one has before. By the time we're done, you won't just walk away with a handful of fascinating theories. You'll see the night sky differently. You'll catch yourself staring at the stars, not just as distant lights, but as clues to a puzzle we're only beginning to solve. Ready to step into the unknown? Let's begin. What if the universe isn't just vast and empty, but humming with invisible conversations? Picture two particles, born from the same cosmic event, separated by millions of light years. Yet when one spins left, the other instantly spins right, as if they're whispering secrets across the void. This is quantum entanglement, a phenomenon so bizarre even Einstein struggled to accept it, dismissing it as spooky action at a distance. But today, we know it's real. And it's not just a quirk of tiny particles, it might be the universe's way of stitching itself together behind the scenes. Think of it like a cosmic game of telephone, except the message doesn't travel through space or time. It just happens faster than light, defying everything we thought we knew about how the universe communicates. Scientists call this non-locality, and it's as close to magic as physics gets. Imagine throwing a pair of gloves into opposite ends of the galaxy. Open one to find the left glove, and instantly the other becomes the right, no matter the distance. That's entanglement in action. So why does this matter? Because if particles can communicate without distance or delay, it hints at a deeper layer of reality, one where separation might be an illusion. Some theorists suggest entanglement could be the foundation of space-time itself, like invisible threads weaving the fabric of the cosmos. Others wonder if it's a clue to hidden dimensions or even a cosmic internet, with particles as nodes in a vast, interconnected network. But here's the real mind bender. What if entanglement isn't the exception, but the rule? What if everything, stars, planets, even you, are subtly entangled, part of a grand, invisible web we're only beginning to detect? It's a humbling thought. The universe might not be a collection of isolated objects, but a single, intricate tapestry, whispering to itself in a language we're just learning to hear. Now, let's shift our gaze to something even more elusive: dark matter, the universe's silent architect. Picture a spiderweb glistening with dew at dawn. You see the droplets catching the light, tracing delicate patterns in the air, but the web itself nearly invisible. That's dark matter, an unseen force holding galaxies together, its presence revealed only by the way it bends the cosmos around it. We've known for decades that something is out there, tugging at stars with invisible fingers. Take the Milky Way. Our galaxy spins so fast that, by all rights, it should fling itself apart. But it doesn't. Something we can't see is holding it together with an unshakable grip. That's dark matter's handiwork. Scientists estimate it makes up about 85% of all matter in the universe. Yet, despite its overwhelming presence, it slips through our detectors like a ghost. So what could it be? The leading theory suggests it's a particle, one that doesn't interact with light or ordinary matter except through gravity. Imagine a crowd of strangers passing through a room. You can't hear them speak, can't see their faces, but you feel the weight of their footsteps shaking the floor. That's how dark matter behaves, but here's where it gets wild. Some researchers think it might not be a particle at all. Could it be primordial black holes, remnants from the birth of the universe? Or something stranger, like a flaw in the fabric of space-time itself? Then there's the radical idea that dark matter isn't matter in the traditional sense. What if it's a shadow cast by another dimension, a hidden layer of reality brushing up against ours? Think of it like ripples on a pond. We see the effects, but the source is just beyond our sight. The deeper we dig, the more questions arise. Why does dark matter cluster in halos around galaxies? Why does it refuse to interact with anything but gravity? Each observation peels back another layer of mystery. And that's the thrilling part. Dark matter isn't just a puzzle to solve. It's a reminder that the universe is far stranger, far richer than our textbooks ever suggested. So next time you look up at the night sky, remember, what you see is just the glittering surface. Beneath it, hidden in the dark, lies an architecture we're only beginning to map, one that might rewrite the rules of reality itself. Black holes have long been the ultimate cosmic enigmas, celestial vacuum cleaners, sucking in everything that crosses their path, never to return. But what if they're not just destructive monsters? What if they're the universe's most sophisticated librarians, meticulously preserving every scrap of information that falls into their grasp? This is the startling idea behind the holographic principle, a theory that turns our understanding of black holes inside out. Imagine tossing a book into a fire. In our everyday experience, the flames would reduce it to ash, obliterating the words forever. But black holes might work differently. According to the holographic principle, every detail of that book, every letter, every page, could be imprinted onto the surface of the black hole's event horizon like a cosmic fingerprint. The event horizon, that invisible point of no return, might not be a one-way street to oblivion. Instead, it could act like a vast celestial hard drive, encoding the information of everything it consumes in a shimmering, two-dimensional hologram. Think of it like a movie projected onto a screen. The images appear three-dimensional, full of depth and movement, but they're actually being generated from flat, two-dimensional data. In the same way, a black hole's event horizon might store all the information about the objects inside it, compressed into an intricate pattern on its surface. This means that nothing truly disappears. It just gets translated into a new, ultra-dense language we're still learning to decipher. So what kind of secrets might these cosmic vaults hold? If the holographic principle is correct, black holes could contain encoded data about the universe's earliest moments, clues about the Big Bang, the formation of galaxies, even the fundamental laws of physics. Some scientists speculate that studying black holes might one day give us a backdoor into understanding quantum gravity, the missing link between Einstein's relativity and the quantum world. But here's where it gets even stranger. If information isn't lost in black holes, it challenges one of the most famous paradoxes in physics, the black hole information paradox. For decades, physicists wrestled with the idea that black holes might permanently erase information, violating a core principle of quantum mechanics. The holographic principle offers a way out, suggesting that information is never truly destroyed, just transformed. Could black holes be the universe's ultimate backup system? If so, they might not just be preserving random cosmic debris, but the very blueprint of reality itself. Every star, every planet, every atom that's ever crossed an event horizon could still exist in some form, etched into the fabric of space-time. It's a humbling thought that even in the darkest corners of the cosmos, nothing is ever truly lost. And that raises one last tantalizing question. If black holes store information so efficiently, could we ever learn to read it? Could we, one day, decode the universe's deepest secrets from the shadows of these cosmic giants? The answer might lie in the faint whispers of Hawking radiation, the subtle glow that black holes emit as they slowly evaporate. Some theories suggest this radiation might carry faint echoes of the information trapped inside, like a message in a bottle drifting out from the edge of oblivion. For now, black holes remain locked vaults, their contents just beyond our reach. But every breakthrough brings us closer to cracking their code, and with it, unlocking the universe's most closely guarded secrets. Time might feel like an unbreakable arrow, always moving forward at the same steady pace, but what if that's just an illusion? Imagine standing knee-deep in a rushing river. The water flows around you, but not all of it moves at the same speed. Near the banks, it slows to a crawl. Around rocks, it swirls into chaotic eddies. This is how some physicists see time, not as a rigid line, but as a fluid dimension, bending and twisting under the weight of gravity, energy, even human perception. Einstein showed us over a century ago that time isn't absolute. The stronger gravity's grip, the slower time ticks. A clock on a mountain runs slightly faster than one at sea level. An astronaut orbiting Earth ages a fraction of a second slower than someone on the ground. These aren't just quirks of relativity, they're clues that time is malleable, a fabric that can stretch, compress, and ripple like water. But here's where it gets stranger. Some theories suggest consciousness itself might influence time's flow. Ever noticed how time drags when you're bored, or races when you're engrossed in something thrilling? This isn't just psychology, it could hint at a deeper connection between mind and the cosmos. In quantum mechanics, the act of observation changes the behavior of particles. Could our awareness also nudge the flow of time, even slightly? Then there's the tantalizing idea of time as a river with hidden currents, ones we might someday navigate. If time is fluid, could we find eddies that loop back on themselves, creating natural wormholes to the past or future? Researchers exploring closed time-like curves, theoretical pathways in space-time that return to their starting point, think it's not entirely impossible. Picture a kayak caught in a whirlpool, circling back to where it began. On a cosmic scale, such loops might exist, woven into the fabric of reality by extreme gravity or exotic matter. But time's fluidity isn't just about travel, it might hide deeper patterns. Ancient cultures tracked celestial cycles, from the wobble of Earth's axis to the slow dance of galaxies. Could these rhythms be echoes of time's true nature, a symphony of waves we're only beginning to hear? Some scientists speculate that universal event supernova, black hole mergers, might leave faint ripples in time itself, like stones dropped into a pond. So what does this mean for us? If time is more river than railroad, mastering its currents could revolutionize everything from computing to cosmology. Quantum computers might one day harness time's flexibility to solve problems in parallel realities. Astronomers could decode gravitational waves not just as ripples in space, but as time's own hidden language. And perhaps most profoundly, it changes how we see our place in the universe. We're not just passengers on time's arrow, we're swimmers in its currents, shaping and shaped by its flow. Every thought, every action might send tiny ripples through the cosmic stream, intertwining our lives with the universe's deepest mysteries. The next time you glance at a clock, remember, those seconds aren't just ticking away. They're bending, twisting, and whispering secrets about the true nature of reality. Have you ever experienced a moment so eerily familiar, it felt like you'd lived it before, not just once, but in some other life, some other version of reality? That unsettling sensation, déjà vu, might be more than just a trick of the mind. What if it's a fleeting echo from a parallel universe, a brief resonance between worlds? This is the spine-tingling idea behind multiverse resonance, the notion that alternate realities aren't just isolated bubbles floating in the cosmic void, but layers of existence that occasionally brush against one another, leaving faint traces in their wake. Picture a grand orchestra with each instrument playing its own melody in perfect isolation. Now imagine those harmonies begin to sync up just for a moment, a single note overlapping between two violins, a chord shared between a piano and a cello. That's how multiverse resonance might work. According to some interpretations of string theory, our universe could be one of countless membranes or brains vibrating in a higher dimensional space. When these brains ripple in just the right way, they might briefly resonate, transferring tiny fragments of information or energy. So what would that look like in our everyday lives? Think of déjà vu as a glitch in the cosmic matrix, a split-second overlap between timelines. Or consider those inexplicable hunches, gut feelings that seem to come from nowhere. Could they be faint signals from alternate versions of ourselves, versions who have already lived the choices we're about to make? Even dreams, those chaotic nightly journeys, might be more than random firings of neurons. Some researchers speculate they could be glimpses into other realities, fragments of lives we're living elsewhere in the multiverse. But here's the twist: resonance isn't just about passive echoes. If parallel worlds can influence one another, even weakly, it raises wild possibilities. Could we, intentionally or not, be sending ripples back and forth? Imagine a version of you in another universe making a pivotal decision, say, pursuing a career in art instead of science. According to resonance theory, that choice might send subtle vibrations across the multiverse, nudging you toward creativity in ways you can't quite explain. It's as if every version of us is part of a vast, interconnected network, each one shaping the others in ways we're only beginning to sense. And then there's the science. Quantum experiments have already shown particles existing in multiple states at once, until observation forces them to choose. What if those unobserved states aren't just probabilities, but actualities playing out in parallel worlds? The famous double-slit experiment, where particles behave as both waves and particles, might not just reveal the quirks of quantum mechanics. It could be a window into the multiverse, with each possible outcome occurring in its own branch of reality. The implications are staggering. If resonance is real, it means no universe is truly alone. Every decision, every chance event might ripple across dimensions, weaving an invisible tapestry of interconnected possibilities. You might never meet your alternate selves face to face, but somewhere in the quiet hum of the cosmos, you're all whispering to one another. So next time you feel that uncanny sense of familiarity, that whisper of another life, don't dismiss it. Pause, listen. The universe might be trying to tell you something, or rather, another version of you might be. What if the universe isn't just expanding? What if it's also cracked? Not in the way a dropped plate shatters, but in something far more subtle and strange. Cosmic strings, hypothetical threads of pure energy thinner than an atom yet stretching across the entire observable universe. Imagine space-time as a pane of glass, smooth and flawless, until a hairline fracture appears, invisible unless you know where to look. That's the eerie elegance of cosmic strings. They wouldn't just sit there either. These defects in the fabric of reality could vibrate, twist, even snap, sending ripples through space-time itself. The idea emerged from the earliest moments of the cosmos. Picture the universe just after the Big Bang, a seething cauldron of energy cooling rapidly as it expanded. As it transitioned from chaos to structure, physicists believe it might have left behind flaws, tiny, frozen imperfections like bubbles trapped in ice. These defects would have stretched impossibly thin as the universe grew, becoming the cosmic strings we theorize today. And if they exist, their influence could be staggering. Take gravity, for instance. A cosmic string wouldn't just warp space, it would slice through it like a knife through fabric, creating a crease so sharp that light bending around it would produce double images of distant galaxies, a phenomenon called gravitational lensing. But here's where it gets wild. Unlike black holes or stars, a string's gravity wouldn't come from mass. It would stem purely from its tension, an intrinsic property making it behave like a cosmic rubber band stretched to its limit. Then there's the tantalizing possibility of shortcuts. Some models suggest that two cosmic strings moving at near light speed could twist space-time around them, forming a closed loop. Step inside that loop, and you might find yourself not just across the room, but across the universe. It's a concept straight out of science fiction, but mathematically sound. These loops could act as natural wormholes, bending the rules of distance without the need for exotic matter or black holes. But how would we find something so elusive? Astronomers have been searching for decades, looking for the telltale signatures, sudden, unexplained shifts in the light of distant quasars, or strange, linear gaps in the cosmic microwave background. Some even speculate that the faintest hum in gravitational wave detectors could one day reveal a string's vibration, a whisper from the dawn of time. Yet the most profound implication isn't just about travel or detection. Cosmic strings could rewrite our understanding of structure in the universe. Galaxies don't form randomly, they cluster along vast web-like filaments. What if those filaments are echoes of cosmic strings, their gravitational influence shaping the cosmos like invisible puppet strings? It's a haunting thought. The largest structures we see might owe their existence to the smallest, most elusive flaws in reality. So the next time you gaze at the night sky, remember, the universe might be far more intricate than it seems, those quiet stretches of darkness between the stars. They could be threaded with cracks, ancient, invisible, and humming with the secrets of creation itself. Right now, as you watch this, trillions of invisible messengers are streaming through your body, not just through the air, but through the floor beneath you, the chair you're sitting on, even the atoms that make up your hands. These are neutrinos, the universe's most elusive particles, so ethereal they can pass through light years of lead without a single collision. But what if these cosmic phantoms aren't just silent spectators? What if they're carrying messages, whispers from exploding stars, or even deliberate signals from civilizations far beyond our own? Neutrinos are born in some of the universe's most violent events. When a star explodes as a supernova, it doesn't just blast light into space, it unleashes a tsunami of neutrinos, outnumbering photons by a factor of billions. In fact, when supernova 1987 lit up the night sky, detectors on Earth picked up a handful of these ghostly particles hours before the light arrived. That's because neutrinos, unlike light, slip effortlessly through the dense debris of a dying star. They're the universe's ultimate couriers, delivering news of cosmic cataclysms almost instantaneously across unimaginable distances. But here's the tantalizing possibility. If neutrinos can carry natural signals, could they also be engineered? Imagine an advanced civilization wanting to broadcast its existence without the interference of dust clouds, black holes, or the noisy chatter of radio waves. Neutrinos would be the perfect medium. They travel in near-perfect straight lines, untouched by magnetic fields or interstellar gas. A neutrino beam could pierce the heart of a galaxy with pinpoint accuracy, a beacon saying, "We're here." And we might already have the tools to listen. Deep underground, in abandoned mines and beneath mountain ranges, scientists have built colossal neutrino detectors, tanks of ultra-pure water or liquid argon surrounded by sensitive photodetectors. When a neutrino finally, rarely interacts with matter, it creates a faint flash of light, a blip in the darkness. These detectors were built to study particle physics, not aliens. But what if, buried in the data, there's a pattern, a sequence of blips too precise to be random? The challenge, of course, is decoding the signal. Neutrinos are notoriously hard to catch and even harder to interpret. But consider this, the very difficulty of detecting them makes a neutrino message inherently secure. Only a civilization with advanced technology could send or receive one, filtering out cosmic noise. It's the ultimate VIP channel, reserved for those who have mastered the universe's subtlest language. So the next time you step outside and look up at the stars, remember, the night sky might not just be a silent spectacle. It could be a bustling network of neutrino conversations, a hidden dialogue woven into the fabric of reality itself. We're only just learning to listen. What if everything around us, the stars, the oceans, even the thoughts in your head, aren't fundamentally real, but lines of code in an unfathomably advanced simulation? This isn't just science fiction. Some of the brightest minds in physics and philosophy take the simulation hypothesis seriously, and their reasoning starts with something we've all experienced: glitches. Think about the strange behavior of particles in the quantum world. Electrons exist in multiple places at once until observed, as if rendering only when needed to save processing power. Light acts as both a particle and a wave, like a graphics engine switching modes for efficiency. Even the speed of light, the universe's maximum processing speed, could be seen as a limit set by the system's hardware. These aren't just quirks, they're potential artifacts of a constructed reality, tiny cracks in the facade where the code shows through. But the most compelling evidence might be math itself. The universe runs on equations so precise they border on perfection. Gravity follows an inverse square law. Electromagnetic forces balance to 19 decimal places. Even chaos has predictable patterns. It's as if reality were designed by a programmer who valued elegance and consistency. Physicist Max Tegmark argues that math isn't just a tool we use to describe the universe, it is the universe, suggesting an underlying computational structure. So who's running the program? One theory points to future civilizations so advanced they've created ancestor simulations, detailed recreations of their own history, with us as unknowing participants. Another possibility, we're experiments in some cosmic lab or even entertainment for beings whose motives we can't begin to fathom, the scariest version. We're NPCs in a game where the players haven't even logged in yet. But here's the real question. If we're in a simulation, can we hack it? Some researchers propose looking for pixelation in the fabric of space-time at the smallest scales. Others suggest hunting for mathematical anomalies, places where the code breaks down, like rounding errors in a cosmic calculator. There's even a fringe idea that quantum entanglement is a networking trick, a way for the simulation to handle long-distance interactions without lag. Yet the most profound implication isn't about proving the hypothesis. It's about what it means for us. If reality is code, then the laws of physics are just parameters waiting to be tweaked. Suddenly, concepts like teleportation or time travel aren't violations of nature, they're undiscovered cheat codes. Consciousness might not be emergent biology, but user input. And death, perhaps just a logout screen. This isn't about despairing that we're not real. It's about realizing that if the universe is programmable, we might one day learn to speak its language, to read the source code, to debug our limitations, even to write our own updates. After all, every simulation needs rules, but rules, as any hacker knows, are made to be bent. There's a silent hum beneath the fabric of reality, a vibration so faint, so constant, we've tuned it out entirely. Empty space, the void between stars and atoms, isn't truly empty. It's a seething ocean of quantum energy, where particles flicker in and out of existence too quickly to be seen, like static on a cosmic radio. This is vacuum energy, the universe's hidden heartbeat, and it might hold the key to unlocking everything from unlimited power to the deepest secrets of existence. Picture a quiet pond at midnight. On the surface, it's perfectly still, but dive beneath and you'll find currents swirling, fish darting, life pulsing in the dark. The vacuum of space is like that pond. What looks like nothingness is actually a frenzy of activity, with particles and antiparticles constantly emerging, colliding, and vanishing in fractions of a nanosecond. These quantum fluctuations aren't just theoretical, they've been measured in labs, with tiny metal plates mysteriously pushed together by the invisible pressure of virtual particles. It's called the Casimir effect, and it's proof that the void is alive with untapped energy. But here's the mind-bending part. This energy isn't just a curiosity. It's everywhere, saturating every cubic centimeter of the universe. Calculations suggest the energy in a single coffee cup's worth of empty space could boil all Earth's oceans. So why aren't we harnessing it? Because vacuum energy is like a wild stallion, powerful, but nearly impossible to tame. Extracting it would mean finding a way to lasso particles that exist for less than a blink, converting their fleeting existence into usable force. Some theorists propose using ultra-fast lasers or quantum mirrors to capture these fluctuations, while others imagine spacecraft powered by the ripples of spacetime itself. Yet the stakes are higher than just clean energy. Vacuum energy might be the driving force behind cosmic expansion, the mysterious dark energy accelerating the universe's growth. If we could manipulate it, we might not just power cities, we could tweak the very expansion rate of reality. Imagine bending space to create warp bubbles for faster-than-light travel, or stabilizing wormholes by reinforcing the quantum foam. The possibilities are as vast as they are perilous. One wrong move, and we might accidentally destabilize spacetime, triggering a catastrophic phase transition. A bubble of new physics expanding at light speed, rewriting the laws of existence as it goes. That's the double-edged sword of vacuum energy. It's a frontier where breakthroughs could redefine civilization or erase it entirely. Laboratories worldwide are already probing this quantum underworld, from ultra-cold atom traps to particle colliders hunting for signs of extra dimensions. Every experiment brings us closer to answering the ultimate question. Is the vacuum a treasure chest waiting to be opened, or a cosmic minefield where one misstep could change everything? So the next time you stare into the night sky, remember, the true mystery isn't just the distant stars. It's the invisible ocean beneath them, crackling with potential, whispering promises of a future we're only beginning to imagine. There's a moment in every quantum physics classroom where students hit the same mental wall when they learn that particles don't settle into a definite state until someone looks at them. It's as if reality holds its breath, suspended between possibilities, until consciousness steps in to cast the deciding vote. This is the observer effect, one of the most baffling and profound discoveries of modern science. But what if it's not just about lab experiments? What if our collective attention, our shared focus, is quietly sculpting the universe at its most fundamental level? Picture a vast, unformed block of marble. Left alone, it's just potential, a chaos of possible shapes. But when a sculptor's hands touch it, chiseling here, smoothing there, it transforms into something specific, something real. Now imagine consciousness as that sculptor and the quantum field as the marble. Every observation, every measurement could be a stroke of the chisel, collapsing infinite probabilities into a single, tangible outcome. The implications are staggering. If a single scientist in a lab can alter particles just by observing them, what might billions of minds do collectively to the fabric of reality? This isn't just philosophical musing. Studies in quantum entanglement show that particles separated by vast distances respond to each other's states instantaneously, as if space and time don't apply to their connection. Some theorists suggest this spooky action might extend to human consciousness, that our thoughts, especially when shared or synchronized, could create ripples in the quantum field. Think of the way a stadium crowd, without speaking, suddenly erupts into the same chant. There's no clear leader, no signal, just a spontaneous alignment of intention. Now scale that up to the cosmic level. Could mass meditation, focused prayer, or even widespread cultural beliefs bend the universe's trajectory in subtle but measurable ways? History offers eerie hints. The placebo effect proves expectation can rewrite biology. Patients given sugar pills often heal as effectively as those on real drugs if they believe they're receiving treatment. If minds can reshape bodies, why not reality itself? Indigenous cultures have long spoken of dreaming the world into being, while modern experiments like the Global Consciousness Project claim to detect statistical anomalies in random number generators during global events, like the Olympics or natural disasters, as if collective emotion leaves fingerprints on data. Yet the boundary between thought and existence remains razor-thin. Skeptics argue correlation isn't causation, and quantum effects don't scale up to everyday life. But consider this, the universe began as a singularity, a point of infinite density where everything was quantum. The large-scale world we see today emerged from those tiny, uncertain rules. If consciousness played a role then, why not now? Here's the radical possibility. Reality isn't a fixed stage, but a living negotiation between observation and possibility. Every choice we make, every story we tell ourselves, might not just reflect the universe, it could define it. That's not mysticism. It's the logical extreme of quantum theory, where the observer isn't separate from the experiment, but part of its very architecture. So the next time you pause to watch a sunset or debate a decision, remember, you're not just a passenger in this universe. You're a participant, a co-creator, whispering into the quantum static, and the universe might just be listening. Black holes dominate our cosmic nightmares, inevitable, all-consuming, inescapable. But what if the universe has an escape clause? Enter white holes, the hypothetical yin to black holes' yang. While black holes trap everything past their event horizon, white holes would do the opposite, violently eject matter and energy, refusing to let anything enter. Picture a cosmic fire hose blasting material outward at impossible speeds, a one-way valve where existence itself gushes into being. The math allows for this. Einstein's equations describing black holes work just as well in reverse, creating a mirror image where time itself flows backward. In theory, a white hole could be a black hole running in rewind, or perhaps something far stranger. Some researchers speculate they might explain the most energetic explosions in the cosmos. When astronomers detect gamma-ray bursts, flashes so powerful they outshine entire galaxies for seconds, could they be witnessing the birth cries of white holes? These bursts defy conventional explanations, appearing without warning and vanishing just as quickly, like cosmic fireworks with no visible fuse, but the wildest idea. White holes might not just eject matter, they could birth entire universes. Imagine a black hole in our cosmos collapsing inward until the pressure becomes unbearable. At some critical point, the singularity might rebound, exploding outward as a white hole in another reality. The matter it spews could form the building blocks of a brand new cosmos, with its own laws of physics, its own dimensions, its own story. This baby universe theory suggests our own Big Bang might have been the white hole eruption of a parent universe's dying black hole. Here's where it gets surreal. If white holes exist, they'd be even more unstable than black holes. Unlike their dark twins, which form from collapsing stars, white holes would require some exotic mechanism to hold them open against the crushing weight of their own gravity. One possibility, quantum effects might briefly stabilize them, like a diver pausing midair before plunging into water. Another theory suggests they could be endpoints for wormholes, tunnels through space-time connecting distant regions, or even separate universes. Step into a black hole here, and you might emerge from a white hole in another time, another place, another reality entirely. Yet for all their theoretical allure, white holes remain ghosts in the equations. No definitive observation has ever confirmed their existence. But absence of evidence isn't evidence of absence, especially when dealing with phenomena that might flicker into being for mere instants before vanishing. Some astronomers hunt for their fingerprints in high-energy cosmic rays or anomalies in the cosmic microwave background. Others simulate their behavior in supercomputers, watching as digital universes give birth to glowing, erupting singularities. The takeaway: white holes remind us that the cosmos might not just be a one-way street toward entropy and darkness. There could be exits, rebirths, cosmic reset buttons woven into the fabric of reality. And if we ever find one, it wouldn't just rewrite astrophysics textbooks, it would redefine our place in the grand, possibly infinite, chain of existence. So the next time you hear about a mysterious energy burst from deep space, keep an open mind. It might not be a dying star. It could be the universe next door saying hello. Gravity feels like the universe's ultimate authority, an invisible hand that pins us to the ground, guides planets in their orbits, and crushes stars into black holes. But what if it's all a grand illusion? Not a fundamental force woven into the fabric of reality, but a side effect, a cosmic mirage emerging from something far stranger. This is the jaw-dropping premise behind gravity's greatest reinvention, the idea that what we perceive as gravity might actually be entropy, the natural tendency of systems to descend into chaos, or even a holographic data projection from the edges of space-time. Start with entropy. Think of a deck of cards fresh from the box, perfectly ordered by suit and number. Shuffle it once and chaos creeps in. Shuffle it 100 times and any trace of the original sequence vanishes. That's entropy in action, the universe's relentless drive toward disorder. Now imagine space-time as a vast, invisible deck of cards. Every object, from a pebble to a planet, disrupts the order around it, creating what we perceive as gravity. Dutch physicist Eric Verlin proposed this radical idea, arguing that gravity isn't a force at all, but a statistical tendency, a byproduct of the universe constantly shuffling its quantum information. Picture standing on a trampoline. The dent your body creates isn't a force pulling objects toward you, it's a deformation of the fabric. In Verlaine's view, gravity works the same way, emerging from the way mass distorts the entropy of space-time itself. But entropy isn't the only contender. Enter the holographic principle, the mind-bending theory that our three-dimensional universe might be a projection of data stored on a two-dimensional surface at its edge, like a cosmic DVD encoding a 3D movie. If true, gravity could simply be how that data interacts, a shadow of deeper processes playing out in a realm we can't see. Imagine typing on a keyboard and watching letters appear on a screen. The keys aren't directly creating the words, they're sending signals to a processor that renders them. Similarly, gravity might not be a standalone force, but the visible output of hidden calculations happening at the universe's boundary. The implications are staggering. If gravity is emergent, not fundamental, Einstein's general relativity, the gold standard for over a century, might be an approximation, a brilliant but incomplete map of deeper terrain. This could explain why relativity and quantum mechanics refuse to play nice. They're describing different layers of the same illusion. Dark matter, the mysterious substance holding galaxies together, might not be missing matter at all, but a miscalculation, a ghost in the equations caused by our misunderstanding of gravity's true nature. Skeptics argue these ideas are untested, and they're right for now. But consider this, when quantum mechanics first emerged, its pioneers faced similar ridicule. Reality, it turns out, has a habit of being far weirder than our intuitions. The hunt for proof is already underway. Some experiments look for subtle deviations in gravity's strength at microscopic scales, where emergent effects might surface. Others simulate holographic universes in supercomputers, watching to see if gravity pops out from the data. Every test brings us closer to answering the ultimate question. Is gravity the universe's rulebook, or just its most convincing magic trick? So the next time you drop a cup and watch it shatter on the floor, don't just blame gravity. Ask yourself, what if that pull you feel isn't a force, but the universe's way of keeping its secrets one entropic shuffle at a time? Take a seashell from the beach and trace the elegant spiral of its growth with your finger. Now zoom way out to the swirling arms of a distant galaxy. At first glance, they couldn't be more different. One fits in your palm, the other spans thousands of light years. But look closer. Both follow the same hypnotic pattern, a curve that grows wider by a precise mathematical ratio with each turn. This is the Fibonacci sequence, a series of numbers where each is the sum of the two before it: 1, 2, 3, 5, 8, and so on, unfolding into the golden ratio, nature's favorite blueprint. The strangest part, this pattern isn't just common, it's everywhere. Sunflower seeds pack themselves in Fibonacci spirals to maximize space. Hurricane clouds swirl in golden ratio perfection. Even the branching veins in a leaf mirror the fractal growth of rivers carving continents. It's as if the universe has a signature, a hidden rhythm it can't help but return to. But why? Is math simply the most efficient way to build things, or is it something deeper, a fingerprint of the cosmos's underlying code? Some scientists argue this prevalence is no accident. The golden ratio emerges from simple rules of growth and competition for space, making it inevitable in systems from biology to astrophysics. But others see a ghost in the machine. The ratio's uncanny precision, approximately 1.618, appears in quantum energy levels, the orbits of planets, even the proportions of the human body. Could these patterns hint at a universe fine-tuned for complexity, even beauty? Then there's the radical idea that math isn't just a tool we use to describe reality, it is reality. The Fibonacci sequence might not just describe spirals, It could be the mechanism generating them, like lines of code executing a cosmic program. Think of a video game rendering a forest. Every tree, every leaf follows algorithms the programmer wrote. In our universe, the golden ratio might serve a similar role, an embedded rule shaping everything from DNA to galaxy clusters. But here's where it gets eerie. The more we look, the more the golden ratio blurs the line between the organic and the engineered. Ancient Greek architects used it to design the Parthenon. Renaissance painters hid it in masterpieces like the Mona Lisa. Even modern stock market analysts find Fibonacci patterns in economic cycles. It's as if this number whispers to us across disciplines, cultures, and epochs, a universal constant tugging at the edges of human creativity. So is the universe a mathematician, a programmer, or is the golden ratio simply the most elegant solution to physics' endless optimization problems? Whatever the answer, one thing's certain. When we find the same numbers in the curl of a fern and the spin of a quasar, we're glimpsing a harmony far older than humanity. The cosmos might not just speak in math, it might think in it, spinning out its secrets one perfect spiral at a time. Magnets are everywhere, sticking notes to your fridge, guiding compass needles north, even humming inside your headphones. But every magnet you've ever encountered has a dirty little secret. It's a fraud. No matter how small you slice it, every magnet has two poles, a north and a south, inseparable as conjoined twins. Cut a bar magnet in half, and you don't get isolated poles, you get two new magnets, each with their own north and south. It's as if the universe refuses to let them divorce. But what if it wasn't always this way? What if, in the searing heat of the Big Bang, single-pole magnets, magnetic monopoles, once roamed free? The idea isn't science fiction. In the late 19th century, physicist Pierre Curie, yes, Marie's husband, first speculated that isolated magnetic charges might exist. Decades later, quantum theory cemented their possibility. Paul Dirac, the legendary physicist who predicted antimatter, showed that monopoles wouldn't just be curiosities, they'd solve one of nature's great asymmetries. Electricity has single charges, electrons negative and protons positive. Why shouldn't magnetism? Dirac even calculated that their existence would neatly explain why electric charge comes in discrete units, like coins in a cosmic vending machine. But here's where the plot thickens. Monopoles aren't just missing puzzle pieces, they might be keys to the universe's first moments. According to grand unified theories, which attempt to merge electromagnetism with the strong and weak nuclear forces, monopoles should have been forged in the unimaginable energies of the early cosmos. These wouldn't be your fridge magnet variety. A single cosmic monopole could be heavier than a battleship, with a magnetic field billions of times stronger than Earth's. They'd be relics of a time when the forces of nature were one, before the universe cooled and fractured them into the rules we know today. So where are they? Despite decades of searching in moon rocks, ancient meteorites, even the debris of particle colliders, monopoles remain ghosts. Some theorists argue they were diluted to near non-existence by cosmic inflation, the universe's explosive expansion moments after the Big Bang. Others suggest they're hiding in plain sight, masquerading as dark matter or lurking in the cores of neutron stars. There's even a fringe idea that monopoles aren't particles at all, but tangled defects in space-time, like knots in an invisible cosmic string. The hunt isn't just academic. Finding a monopole would do more than fill a textbook gap. It could rewrite physics. Their existence would imply new symmetries in nature, hint at hidden dimensions, or even reveal how to unify quantum mechanics with gravity. Some models suggest monopoles could catalyze proton decay, turning ordinary matter into pure energy. Imagine a speck of dust that, if dropped into a glass of water, could make it vanish in a flash of light. That's the power we're talking about, yet the most tantalizing clue might lie in the cosmos itself. If monopoles were abundant in the infant universe, their gravity could have seeded the first galaxies, their magnetic fields sculpting the cosmic web we see today. Their absence, ironically, might explain why inflation happened at all, a cosmic cleanup erasing their excess. Every failed search narrows the possibilities, forcing us to ask, is nature teasing us with a pattern it refuses to complete, or are we just not looking hard enough? So the next time you pick up a magnet, remember, you're holding half of a cosmic love story, a partnership so fundamental we've never seen it broken. But somewhere in the vastness of space or the depths of a lab, its other half might be waiting a solitary north or south, whispering secrets about the universe's fiery birth. Imagine a ball rolling up a hill, except halfway up, it suddenly appears on the other side without ever reaching the top. That's quantum tunneling in action, the bizarre phenomenon where particles cheat their way through barriers they shouldn't be able to cross. It's not magic, it's quantum mechanics at its most mischievous, and it might be the universe's favorite shortcut. At the subatomic level, particles don't behave like billiard balls. They're more like clouds of probability, flickering in and out of existence in a haze of uncertainty. When one encounters a wall, whether it's an electric field or the crushing pressure inside a star, there's a tiny but real chance it'll simply appear on the other side, as if the barrier weren't there at all. It's like rolling a die and watching it vanish from your hand only to materialize across the room. The odds are low, but in a universe teeming with particles, unlikely events happen constantly. Now zoom out to the cosmic scale. Inside stars like our Sun, hydrogen nuclei must overcome their mutual repulsion to fuse and release energy. The problem: their positive charges should keep them far apart, like magnets pushing against each other. But thanks to quantum tunneling, protons occasionally bypass that barrier entirely, allowing fusion to ignite. Without this quantum quirk, stars might never shine, and the universe would be a dark, lifeless void. But tunneling's role doesn't stop there. Some theories suggest it could explain even grander phenomena. Take black holes. According to Stephen Hawking, they slowly evaporate by emitting radiation, a process that relies on particles tunneling out of their gravitational grip. On an even wilder note, some cosmologists propose that the Big Bang itself might have been a quantum tunneling event, a spontaneous leap from nothingness into existence. Picture a marble resting in a bowl stable, motionless. Now imagine it suddenly appearing in a second bowl nearby without rolling over the edge. If the universe began this way, it wouldn't need a traditional cause, just the right quantum fluctuation. Here's the twist: tunneling might not just be a feature of reality, it could be a tool. Scientists are already harnessing it in quantum computers, where particles tunnel through barriers to perform calculations faster than any silicon chip. Future technologies might use tunneling to create ultra-efficient energy systems or even teleport materials through solid walls. Nature's been doing this for billions of years, we're just catching up. So the next time you feel stuck, remember, even the universe knows how to bend the rules. From the smallest particles to the grandest cosmic events, quantum tunneling whispers a rebellious truth that barriers are only as solid as probability allows. And in a reality this strange, who knows what's on the other side? Imagine waking up one day with all your memories intact, your childhood, your first love, even what you ate for breakfast, only to realize none of it ever happened. You're not a person, not even a body, but a lone, self-aware brain that spontaneously assembled from the random jostling of atoms in the void. This isn't the plot of a sci-fi nightmare. It's the Boltzmann brain paradox, a thought experiment so unsettling it makes the simulation hypothesis seem almost comforting. The idea comes from Ludwig Boltzmann, the 19th century physicist who helped pioneer statistical mechanics. He realized that in an infinite universe, even the most improbable events must happen eventually given enough time. Monkeys typing randomly could produce Shakespeare's works. Now scale that up. In a cosmos that's existed for billions of years with particles ceaselessly colliding, isn't it statistically inevitable that, somewhere, atoms would randomly arrange themselves into a conscious mind? Not a brain born of evolution, not a product of a universe teeming with life, but a solitary, fully formed consciousness blinking into existence, complete with false memories of a past that never was. Here's where it gets dizzying. If Boltzmann brains are possible, they're almost certainly more common than ordinary brains like ours. Think about it. Crafting an entire universe with galaxies, planets, and civilizations is astronomically more complex than assembling a single, self-aware mind floating in the dark. So by sheer probability, you are far more likely to be a Boltzmann brain hallucinating reality than a real person in a real universe. Every memory, every sensation, even the screen you're staring at right now, could all be an elaborate illusion conjured by particles that just happen to collide the right way. But wait, wouldn't such a brain instantly dissolve back into chaos? Not necessarily. Quantum fluctuations can create particles out of empty space, a phenomenon we've observed in labs. In an eternal cosmos, even a fleeting moment of consciousness is enough to ask, "Am I real?" before vanishing. Some versions of the paradox suggest these brains might persist longer if they hallucinate a stable, consistent reality, like a dreamer convinced they're awake. So why hasn't science dismissed this as philosophical nonsense? Because the paradox exposes a terrifying flaw in our understanding of cosmology. If the universe truly is infinite and eternal, Boltzmann brains aren't just possible, they're inevitable. That means our entire reality could be a statistical fluke, with true, objective existence vanishingly rare. Some physicists argue this is evidence for a cosmological model that prevents such fluctuations, like a universe with a finite lifespan or one fine tune to avoid random consciousness. Others take it as proof we're missing something fundamental about time, entropy, or the nature of observation itself. The most haunting question isn't whether Boltzmann brains exist. It's whether we can ever know they don't. Every piece of evidence you might use to prove your reality, scientific laws, historical records, even your own thoughts, could be part of the illusion. The paradox doesn't just challenge our place in the cosmos, it pulls the rug out from under reality itself, leaving us with no solid ground to stand on. Yet there's a strange beauty in this madness. If the universe can conjure consciousness from chaos, even briefly, then awareness might not be a biological accident but a latent property of existence, waiting to emerge wherever conditions allow. Boltzmann brains are either the ultimate cosmic prank or a clue that mind and matter are far more deeply entwined than we ever imagined. So the next time you second-guess a memory or déjà vu sends a shiver down your spine, consider this: you might not be questioning your past. You might be glimpsing the void's quiet whisper that in an infinite cosmos, even the impossible gets its turn. Every galaxy in the cosmos is racing away from every other, not just moving but accelerating, as if space itself is stretching faster with each passing moment. This isn't just expansion, it's a runaway cosmic sprint fueled by something invisible, something relentless: dark energy. Unlike gravity's familiar pull, dark energy pushes, an anti-gravity force woven into the fabric of empty space itself. But here's what keeps cosmologists awake at night. What if this force isn't just strange but unstable? What if the very engine driving the universe's growth could one day throttle up or snap shut? Let's rewind to the late 1990s when astronomers made a discovery that shattered expectations. By measuring distant supernova, they found the universe wasn't just expanding, it was doing so faster than ever before. The culprit, dark energy, a mysterious presence making up roughly 68% of the cosmos. Picture a balloon inflating, but instead of slowing down as it grows, it's being pumped with more and more air against all logic. That's dark energy's handiwork, except the balloon is reality itself, and no one knows where the pump came from. The simplest explanation is the cosmological constant, an idea Einstein once proposed and later dismissed as his greatest blunder. It suggests dark energy's strength never changes, a steady pressure embedded in space. But what if that's wrong? Some theories propose dark energy could evolve over time, growing stronger or weaker. Imagine a car's gas pedal stuck in two possible positions. Either it gradually sinks to the floor, sending the universe into hyperdrive, or it suddenly releases, slamming the brakes on expansion. The first scenario, the Big Rip, is as horrifying as it sounds. If dark energy's repulsion grows unchecked, it wouldn't just push galaxies apart, it would tear them apart. Stars, planets, even atoms would be shredded as space stretches faster than the forces holding matter together. The cosmos would end not with a bang or a whimper, but a silent, infinite unraveling. The opposite extreme, the Big Crunch. If dark energy weakens, gravity could regain dominance, reversing expansion. Galaxies would hurtle toward one another, colliding in a fiery collapse that culminates in a singularity, a mirror image of the Big Bang. Some models even suggest this could trigger a cyclical universe, where collapse and rebirth loop eternally. But the most unsettling possibility is that dark energy isn't a constant or a gradual variable, it's a ticking clock. Quantum field theory allows for metastable vacuum states, where what we call empty space is actually a false equilibrium. Like a ball balanced precariously on a hill, a nudge could send it tumbling into a lower energy state. If this happened, a bubble of true vacuum could form, expanding at light speed, rewriting the laws of physics as it goes. One moment, the universe operates as usual. The next, chemistry, light, even time itself could cease to function as we know it. The stakes couldn't be higher. Dark energy isn't just a curiosity, it's the architect of the universe's ultimate fate. Current telescopes like Euclid and the upcoming Nancy Grace Roman Space Telescope are hunting for clues, mapping how dark energy's influence has changed over cosmic history. Every measurement tightens the noose around these theories, inching us closer to knowing whether we're headed for a slow fade, a violent end, or something stranger still. So the next time you gaze at the night sky, remember, the vast emptiness between stars isn't passive. It's alive with a force we barely understand, one that could already be shifting beneath our feet, or rather, beneath the fabric of everything. What if our universe wasn't born from a single, fiery explosion, but from a quiet, cataclysmic embrace? Picture two sheets of paper floating in an endless dark room. They drift closer, inch by inch, until contact. A shudder ripples through both, sending vibrations racing across their surfaces. Now imagine those sheets aren't paper, but vast, shimmering membranes, higher dimensional planes called brains, and their collision doesn't just make noise. It births reality itself. This is the ekpyrotic universe theory, a radical rewrite of cosmic origins where the Big Bang wasn't the beginning, but just the latest chapter in an endless cycle of collisions, rebirths, and resets. The name ekpyrotic comes from the Greek word for conflagration, but don't let that fool you. Unlike the chaotic fury of the traditional Big Bang, this model paints a strangely elegant picture. Our three-dimensional universe might be embedded in a higher dimensional space, like a leaf suspended in a pond. Floating nearby, another brain, perhaps a parallel universe, draws inexorably closer over billions of years. When they meet, the impact unleashes enough energy to forge galaxies, stars, and planets, but without the infinite heat and density of a singularity. It's less a bang and more a cosmic tap on the shoulder, a whisper saying, "Again." Here's where it gets mesmerizing. After the collision, the brains rebound, stretching apart and cooling into a new universe, ours. Matter condenses, gravity sculpts galaxies, and life emerges. But the story doesn't end there. The brains, still drifting in their higher dimensional sea, eventually stop, and begin falling toward one another once more. Billions of years from now, they'll collide again, triggering another rebirth. No beginning, no end, just an infinite dance of creation and destruction, each cycle subtly different from the last. Why would anyone trade the simplicity of the Big Bang for such an elaborate waltz? For one, it solves some of cosmology's stickiest puzzles. The traditional model struggles to explain why the universe is so uniform, why the cosmic microwave background, the afterglow of the Big Bang, looks almost identical in all directions. Inflation theory proposes a rapid expansion to smooth things out, but the ekpyrotic model offers a cleaner fix. The slow, steady approach of the brains before collision naturally evens out irregularities, like rolling dough to erase lumps. Then there's the dark energy riddle. If the universe's expansion is accelerating, could it be the brains already beginning their next approach, their gravitational pull subtly bending space-time? Some versions of the theory even suggest that the mysterious dark matter halos around galaxies are fingerprints of the higher dimensional geometry, shadows cast by the unseen brain. But the most profound implication isn't just about physics, it's about time. In this model, the arrow of time might flip with each cycle. Entropy, the measure of disorder that gives time its direction, could reset at every collision, meaning the past before the Big Bang might actually be a mirror of our future, a universe collapsing toward the next rebirth. Imagine watching a film of the cosmos, play it forward, and you see stars forming, civilizations rising. Rewind it, and you're not seeing destruction. You're witnessing the prelude to another beginning. Of course, the theory isn't without skeptics. Without direct evidence of higher dimensions or parallel brains, it remains a beautiful hypothesis, but hidden in the math are potential clues. If the collision sent ripples through space-time, they might still echo in the cosmic microwave background or gravitational waves. Future telescopes, tuned to the faintest whispers of the early universe, could one day catch these ghostly vibrations, a signature of the brain that birthed us. So the next time you hear about the Big Bang, remember, it might not have been the first, and if the ekpyrotic model is right, it certainly won't be the last. Our universe could be just one note in an infinite symphony, a single verse in a song the cosmos has been singing forever. At the heart of a neutron star, matter doesn't just get squeezed, it breaks. Imagine taking the entire mass of our sun and crushing it into a sphere the size of Manhattan. The gravity is so intense that atoms collapse, electrons fuse with protons, and what remains is a sea of neutrons packed tighter than sardines in a cosmic can. But even this mind-bending density might just be the surface of the mystery. Dig deeper, past the crushing outer layers, and things get stranger. Some theories suggest the cores of these stellar corpses could harbor matter so exotic, it defies every textbook definition of solid, liquid, or gas. We're talking about quark-gluon plasma, a primordial soup where protons and neutrons dissolve into their fundamental particles, swirling in a state last seen microseconds after the Big Bang. Now picture this soup freezing into something even wilder, a time crystal, unlike ordinary crystals which repeat their structure in space, time crystals repeat in time, oscillating between states without any energy input. It's like a clock that ticks forever without winding, a perpetual motion machine woven into the fabric of reality. If neutron star cores contain these bizarre structures, they'd be the most perfect timekeepers in the universe, their rhythms untouched by entropy or decay. But how would we ever know? Neutron stars don't exactly come with windows. The answer might lie in their death throes. When two neutron stars collide, the resulting kilonova explosion sprays heavy elements like gold and platinum across space, but it could also unleash a burst of gravitational waves, ripples in space-time carrying fingerprints of the star's internal composition. In 2017, detectors on Earth picked up such waves from a neutron-star merger. Hidden in that signal might be clues about the core's exotic physics, like echoes from a vault we're just learning to crack. Then there's the puzzle of pulsars, neutron stars that beam radiation like cosmic lighthouses with freakish precision. Some spin hundreds of times per second without slowing down, their stability defying conventional physics. Could quark matter or time crystals explain their perfect rhythms? Or is there something even stranger at play, like hyperfluid vortices where friction vanishes entirely? The wildest possibility, these cores might house states of matter we haven't even named yet. Under pressures 100 trillion times Earth's atmosphere and temperatures 1,000,000 times the Sun's surface, matter could fold into higher dimensions, form quantum knots that never untangle, or even create temporary wormholes in the quantum foam. Every extreme in nature births new rules, and neutron stars are the ultimate laboratory for the physics we've never dared to imagine. So the next time you spot a pulsar's flicker in the night sky, remember, that tiny pinprick of light might be the tip of an iceberg, a cosmic Rosetta Stone hiding the universe's most guarded secrets. And we're just beginning to decipher its language. Imagine stepping into a movie theater, slipping on 3D glasses, and suddenly feeling the explosions rattle your seat as objects seem to leap off the screen. Now picture this. What if our entire universe is that movie, a dazzling three-dimensional illusion projected from a flat, two-dimensional surface trillions of light years away? This isn't science fiction, it's the holographic principle, one of the most radical ideas in modern physics, suggesting that everything we see, touch, and experience might be nothing more than an incredibly convincing cosmic mirage. The roots of this theory stretch back to black holes. In the 1970s, physicist Jacob Bekenstein discovered something astonishing. The maximum amount of information a black hole can contain isn't proportional to its volume, as you'd expect, but to the surface area of its event horizon. It's as if the black hole's three-dimensional interior was somehow encoded on its two-dimensional boundary, like a DVD storing a 3D movie on a flat disk. Decades later, string theorists took this further, proposing that our entire universe could operate the same way. Every star, every planet, even your own thoughts, might be pixels in a hologram with the real data of reality imprinted on a distant, flat surface we can't see or touch. But where is this cosmic projector? Some theories point to the edge of the observable universe, where space-time stretches into infinity. Others suggest it's hiding in extra dimensions, curled up so tightly we'd never perceive them. The wildest possibility, the projector isn't out there at all, it's us. Consciousness itself might play a role in rendering the hologram, collapsing quantum possibilities into the solid world we experience. Think of it like a video game that only generates graphics when you look at them, conserving processing power. If the universe works similarly, our observations could be the very thing that makes it real. This isn't just wild speculation. Experiments are already hunting for proof. Fermilab's holometer, for instance, searches for telltale pixelation in space-time itself. tiny vibrations that would betray the universe's underlying grid. Meanwhile, studies of cosmic microwave background radiation look for anomalies in the way light scatters across the sky, potential fingerprints of holographic encoding. Even quantum entanglement, where particles remain mysteriously linked across vast distances, might make more sense if they're projections of the same underlying code. The implications are staggering. If the holographic principle is true, it means that black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate hard drives. It means that gravity, the force that shapes galaxies, might emerge from information theory, not geometry. And it raises the eerie possibility that other holograms, other universes, could be projected from surfaces we'll never reach, like infinite movies playing side by side in a cosmic multiplex. So the next time you hold your phone, feel the wind, or watch a sunset, consider this. You might not be interacting with objects at all, but with shadows on the wall of a deeper reality. The universe isn't just stranger than we imagine. It might be stranger than we can imagine, a hologram so perfect, we'll spend centuries learning to see the edges of the frame. Wormholes have long been the stuff of science fiction cosmic shortcuts, connecting distant corners of the universe in the blink of an eye. But what if these theoretical tunnels through space-time aren't just plot devices for interstellar adventures? What if they're real, lurking in the equations of general relativity, waiting for us to uncover their secrets? Einstein and physicist Nathan Rosen first theorized them in 1935 as bridges between 2 points in spacetime structures, now called Einstein-Rosen bridges. Yet for decades, they seemed like mathematical curiosities, requiring exotic matter with negative energy to stay open, a substance so bizarre it defies everything we know about physics. But here's the twist: nature has a habit of surprising us. Recent breakthroughs suggest wormholes might not need impossible energies after all. Quantum physics introduces wild possibilities, like Casimir cavities, tiny regions where quantum fluctuations create negative energy densities. Scale this up, and suddenly, propping open a wormhole doesn't seem quite so far-fetched. Some models even propose that rotating wormholes could stabilize themselves using only ordinary matter, their centrifugal force acting like a cosmic drawbridge. Then there's the time travel angle. If a wormhole's mouths move relative to each other, say, one near a black hole where time slows to a crawl passing through, could catapult you not just across space, but across centuries. Picture stepping into a tunnel on Earth and emerging near a distant star in the year 3000, or the Jurassic. The catch: any attempt to alter the past might trigger paradoxes that unravel the wormhole itself, like a circuit overloading from feedback. But the most tantalizing idea isn't just about traversing wormholes, it's about growing them. Some theorists suggest microscopic wormholes could have formed in the chaos of the early universe, frozen in the quantum foam. With the right technology, we might one day inflate them, like blowing up a balloon, until they're large enough to traverse. It's a long shot, but so was splitting the atom, until we did it. So are wormholes cosmic rarities, or hidden highways woven into the fabric of reality? The answer might lie in the ripples of gravitational waves or the quantum whispers of particles flickering in and out of existence. Until then, they remain the universe's ultimate what-if bridges to worlds we've yet to imagine. Imagine Earth not just as a rock hurtling through space, but as a vast, breathing entity, a planet that doesn't merely harbor life, but behaves like a living system itself. This is the heart of the Gaia Hypothesis, the provocative idea that our planet functions as a single, self-regulating organism. Picture the way your body sweats to cool down in summer or shivers to generate heat in winter. Now scale that up to a planetary level. forests regulating carbon dioxide, oceans balancing salinity, even microbes in the soil fine-tuning atmospheric chemistry. It's as if Earth has its own pulse, a rhythm of feedback loops that maintain the delicate conditions for life against all odds. But why stop at Earth? If one planet can exhibit these lifelike qualities, what about the rest of the cosmos? Stars, for instance, might seem like unthinking fusion reactors, but their behavior is eerily precise. Take our Sun. It's not just a random ball of plasma. Over billions of years, it's gradually increased its brightness, yet Earth's temperature has remained relatively stable. Coincidence, or could stars and planets be engaged in a slow, cosmic dance of mutual regulation? Some astronomers speculate that galaxies, too, might function like vast neural networks, with supermassive black holes acting as central nodes that influence the growth and movement of stars around them, almost like a brain coordinating its cells. Then there's the eerie synchrony of cosmic cycles. On Earth, phytoplankton blooms follow seasonal rhythms so precise they can be seen from space, painting the oceans with living swirls. Now look outward. Pulsars emit radio waves with clockwork regularity, and galaxies spin in patterns that defy random chance. Could these be signs of larger, unrecognized systems at work? The universe is full of structures that mimic biological ones, filaments of galaxies resembling neurons, galaxy clusters mirroring cellular networks. If life on Earth emerged from simple chemistry, why couldn't complexity arise on scales we've barely begun to fathom? Critics argue this is anthropomorphism, projecting earthly concepts onto the cold, mechanical universe. But the counterpoint is equally compelling. We once thought Earth was unique in its ability to host life, until we found extremophiles thriving in volcanic vents and frozen tundras. If life can adapt to such extremes here, why couldn't the universe harbor other, unimaginable forms of aliveness? Some theorists even suggest that dark matter, the invisible scaffolding of the cosmos, could play a role in these grand systems, like the unseen mycelium networks that connect forests underground. The Gaia Hypothesis forces us to confront a radical question. What if life isn't something that happens on a planet, but to a planet? And if that's true, then the universe might not be a sterile void dotted with rare oases of biology. It could be a living, evolving entity in its own right, with planets as cells, stars as energy sources, and galaxies as sprawling, interconnected ecosystems. So the next time you feel the wind on your face or watch the tides roll in, remember, you're not just standing on a planet, you're part of its rhythm, a heartbeat in a system far grander than we've yet dared to imagine. And if Earth can hum with this invisible harmony, who's to say the rest of the cosmos isn't singing too? Consider how life evolves on Earth. Only the fittest traits survive, passed down through generations in an endless refinement of biology. Now imagine the same principle applied not to living creatures, but to the very fabric of reality. This is the startling premise of quantum Darwinism, the idea that the universe itself might be subject to a kind of cosmic natural selection, where only the most stable quantum states survive observation while others fade into oblivion. Think of a quantum particle existing in a haze of probabilities spinning both clockwise and counterclockwise, here and there, until the moment someone looks. At that instant, its wave function collapses into a single, definite state. But why that state and not another? Quantum Darwinism suggests it's not random. Just as environmental pressures favor certain genes, the act of observation might favor certain quantum outcomes based on their ability to persist and replicate information. The most stable, robust configurations, those least likely to decohere under scrutiny, are the ones we ultimately perceive. This isn't just about particles in a lab. Zoom out and the implications become cosmic. If quantum states are selected for stability, could the laws of physics themselves be the result of a much larger evolutionary process? Picture the early universe as a bubbling quantum soup, where countless potential laws of nature flickered in and out of existence. Most collapsed instantly, too unstable to endure. But a few, like the finely tuned constants governing gravity or electromagnetism, were resilient enough to persist, forming the framework of reality as we know it. In this view, our universe isn't just governed by laws, it's shaped by them, honed over eons of quantum selection. Here's where it gets even wilder. If the universe evolves its own rules, there's no guarantee they're fixed forever. Some theories propose that physical laws could subtly shift over time, adapting to new conditions like a living organism. Dark energy's accelerating expansion might not be a constant force, but evidence of this slow cosmic adaptation. Even the emergence of life, with its ability to observe and interact with quantum systems, could be part of the universe's way of stabilizing itself, like a self-reinforcing loop where observation begets more stable states, which in turn enable more complex observers. Critics argue this veers into philosophy, blurring the line between metaphor and mechanism. Yet experiments are already hinting at its plausibility. When quantum systems are repeatedly measured, certain states do appear more frequently, as if selected by the environment. Researchers call this quantum jumps, but it's eerily reminiscent of survival of the fittest, just at a scale smaller than atoms. The most profound question isn't whether quantum Darwinism is true, but what it means for our place in the cosmos. If reality evolves, are we merely passengers on the ride or active participants in its unfolding? Every observation, every experiment might not just be uncovering the universe's rules, it could be shaping them, one quantum decision at a time. So the next time you look at the stars, consider this. The laws that let them shine might not be eternal truths, but the winners of a cosmic competition, and the game's still being played. Imagine the universe as a vast sheet of paper, slowly stretching in all directions. Now picture that stretching speeding up, not just pulling galaxies apart, but wrenching planets from their orbits, tearing stars to shreds, even ripping atoms into their fundamental particles. This isn't just cosmic expansion, it's the Big Rip, a theoretical doomsday scenario where dark energy doesn't just push, but escalates into an unstoppable force, unraveling reality itself. And the culprit, phantom energy, a hypothetical form of dark energy so destructive, it makes black holes look gentle. Phantom energy isn't your average cosmic fuel. Ordinary dark energy, as mysterious as it is, behaves like a steady pressure Einstein's cosmological constant. But phantom energy is darker. Its density increases over time, its repulsive force growing stronger as space stretches. Think of it like a car's gas pedal jammed permanently to the floor. At first, expansion seems manageable, but eventually, the acceleration becomes uncontrollable, overwhelming gravity, then electromagnetism, then even the nuclear forces holding atoms together. The universe wouldn't just fade, it would explode from within, disintegrating into a sea of lonely quarks and neutrinos. The timeline, that's where it gets chilling. Current observations suggest dark energy's equation of state. A measure of its pressure-to-density ratio hovers close to -1, the signature of a cosmological constant. But what if it's slightly more negative, crossing into phantom territory? Some models place the Big Rip just tens of billions of years away. Others, if phantom energy's growth is exponential, speculate it could happen shockingly soon within a cosmic blink. Imagine a countdown clock where the numbers suddenly start racing backward. Yet here's the twist, phantom energy might not just be a doom, it could be a clue. If it exists, its behavior would hint at undiscovered physics, perhaps extra dimensions or a flaw in Einstein's equations. Some theorists even propose it's a sign of vacuum decay, where our universe's false vacuum state collapses into a lower energy configuration, rewriting the laws of physics in an expanding bubble of annihilation. Could we stop it? Unlikely, but understanding it might be our greatest insurance. Telescopes like the Vera Rubin Observatory are mapping dark energy's evolution with unprecedented precision, hunting for deviations that might signal a phantom uprising. Every decimal point in the data could mean the difference between a universe that expands forever and one that shreds itself to bits. So the next time you hear about dark energy, remember, it's not just pushing galaxies away. It might be winding the clock on existence itself, and we're only beginning to read the time. There's a rule so fundamental to physics, it's practically gospel: information cannot be destroyed. Burn a book and the ashes might seem like chaos, but in theory, every word, every letter could be reconstructed from the smoke and residue. Now imagine tossing that book into a black hole. According to Einstein's general relativity, it's gone forever, crushed into the singularity's infinite density. But quantum mechanics insists the information must still exist somewhere, encoded in the fabric of reality. This is the black hole information paradox, a clash of titans between our two most successful scientific theories, and the key to unlocking a deeper truth about the universe. At first glance, the paradox seems simple. Black holes evaporate over time, thanks to Hawking radiation, a slow leak of energy that eventually causes them to vanish. But here's the catch: Hawking radiation appears random, carrying no trace of the matter that fell in. If the black hole disappears, where did the information go? It's like shredding a document and then burning the scraps, only to realize the ashes contain no hint of the original text. Quantum mechanics says this can't happen. Information is immortal, so either Einstein's relativity is missing something or quantum theory is incomplete. The stakes couldn't be higher. If information can vanish, it undermines the predictability of the universe, the very foundation of physics. Imagine a detective trying to solve a crime where the evidence literally winks out of existence. No cause, no effect, just gaps in the story of reality. This is why Stephen Hawking famously bet against information preservation in black holes, only to concede decades later when new math suggested a way out. Enter the holographic principle. If a black hole's event horizon encodes falling information like a cosmic hard drive, preserving it in two-dimensional pixels on its surface, then nothing is truly lost. The information isn't inside the black hole, it's smeared across its boundary, scrambled but intact. Think of it like a movie projected onto a screen. The images seem three-dimensional, but they're actually rendered from flat data. Similarly, the three-dimensional universe we experience might be a projection of information stored at its edges. But how does the information escape? Hawking radiation might not be so random after all. Recent breakthroughs suggest it could carry subtle fingerprints of what fell in, like smoke particles preserving the shape of the fire that created them. This soft hair theory proposes that black holes leave faint imprints in spacetime, invisible quantum strands that record incoming matter. Over eons, as the black hole evaporates, these imprints could slowly leak the information back out, like a sealed letter finally opened. The wildest twist, this paradox might not just be about black holes. If information is truly preserved at the quantum level, it could mean the universe has a built-in backup system, a cosmic redundancy that ensures nothing is ever truly erased. Every particle, every interaction might leave an eternal mark on the fabric of reality, like ripples in a pond that never fully fade. So the next time you delete a file or toss out an old notebook, remember, the universe doesn't have a trash bin. Information sticks around, even in the darkest corners of existence. And solving this paradox won't just tell us where it goes, it could reveal the hidden language that binds quantum mechanics and relativity into a single, unified theory of everything. Rising from the heart of our Milky Way like twin zeppelins of pure energy, the Fermi bubbles stretch 50,000 light-years above and below the galactic plane, a pair of colossal gamma-ray emitting structures so vast they dwarf the entire visible disk of our galaxy. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these hourglass-shaped formations glow with the aftermath of some unimaginable cataclysm, their origins shrouded in mystery. What cosmic event could have unleashed such titanic structures, and why do their edges crackle with energy millions of years after their birth? The leading theory points to Sagittarius A, the supermassive black hole at our galaxy's center. Picture this: 4 million suns worth of matter crammed into a space smaller than our solar system. Now imagine it waking from its slumber, devouring a passing gas cloud or star in an epic feeding frenzy. The resulting energy would blast outward along the galaxy's rotational axis, creating shock waves that accelerate particles to near light speeds, a phenomenon astronomers call a black hole belch. These particle jets could have inflated the bubbles like cosmic balloons, their surfaces still shimmering with gamma rays from ongoing particle collisions. But there's a problem with this neat explanation. The bubble's razor-sharp edges and symmetrical structure suggest an eruption far more focused and violent than typical black hole activity. Some researchers propose an alternative culprit, a runaway starburst event where hundreds of massive stars formed and exploded in rapid succession near the galactic center. The combined supernova could have pumped enough energy into the interstellar medium to create these enormous cavities like stomping on a cosmic soda can until it pops outward in perfect hemispheres. Then there's the wild card dark matter annihilation. If hypothetical weakly interacting massive particles WIMP exist, their collisions in the galaxy's dense core might release bursts of gamma radiation, potentially sculpting the bubbles over eons. It's a long shot, but the bubble's uniform emission pattern matches certain dark matter models better than traditional astrophysical sources. The most tantalizing clue lies in the bubble's microwave haze, a fog of polarized radio waves that perfectly aligns with their gamma-ray structure. This suggests the original event wasn't a single cataclysm, but an ongoing process like a black hole's intermittent outbursts or a slow-burning dark matter reaction. Upcoming observations from next-generation telescopes like CTA-Cherenkov Telescope Array could detect ultra-high-energy gamma rays from the bubble rims, potentially revealing whether the culprit was a one-time feast or a still hungry beast. What makes the Fermi bubbles truly extraordinary isn't just their scale, but their timing. Based on their expansion rate, these structures likely formed between 2 and 4 million years ago, around the same time our early human ancestors first walked upright. For a galaxy that's 13 billion years old, this was practically yesterday. Whatever created them wasn't some ancient relic. It was a recent, violent chapter in our Milky Way's biography, one that might not be over yet. So the next time you gaze toward the constellation Sagittarius, remember, hidden in that direction, invisible to our eyes but pulsing with high-energy light, two colossal reminders loom that our galactic home is anything but quiet. The Fermi bubbles aren't just fossils, they're a warning, a monument, and perhaps a preview of the next cosmic upheaval waiting in our galaxy's core. The cosmic microwave background, the afterglow of the Big Bang, should be the ultimate cosmic equalizer, a perfectly uniform canvas of ancient light stretched across the entire sky. That's what the foundational cosmological principle demands: no preferred direction, no special place in the universe, but But in 2005, astronomers stumbled upon something that shattered this assumption. Dubbed the axis of evil, it's a bizarre alignment in the CMB's temperature fluctuations that points like a compass needle toward a specific region of space, as if the universe itself has a North Star. This isn't just a statistical fluke. The odds of such a pattern arising by chance are less than 1 in 1,000 cosmic roulette where the ball keeps landing on the same number. So what could possibly explain this cosmic faux pas? One possibility cuts straight to the bone of modern cosmology. We've misunderstood the Big Bang. The Standard Model assumes inflation, a rapid exponential expansion of space, smoothed the early universe into uniformity. But if inflation didn't happen quite as we thought, or if it left behind primordial textures in spacetime, these could imprint directional biases on the CMB. Imagine blowing up a balloon with slight wrinkles. No matter how much you inflate it, those imperfections persist. The axis of evil might be one such wrinkle, a fossilized relic of the universe's first trillionth of a second. Then there's the multiverse angle. If our universe is one bubble in a vast foam of others, its collision with a neighboring bubble could have warped the CMB, leaving a directional bruise. Picture two soap bubbles merging. The point where they touch forms a distinct ridge. On a cosmic scale, such an event would create asymmetries precisely like the axis of evil, a scar from a long-ago encounter with another reality. But the most unsettling explanation, we're seeing the shadow of something far larger. Just as the gravitational pull of the Great Attractor distorts the motion of galaxies across hundreds of millions of light years, an unimaginably vast structure beyond our observable horizon could be tugging on the fabric of spacetime, skewing the CMB's uniformity. This wouldn't just violate the cosmological principle, it would imply the universe is fundamentally lopsided, with our observable patch merely a backwater in an infinite, uneven cosmos. The irony is delicious. The CMB, once hailed as proof of cosmic democracy, might instead reveal the universe's secret hierarchy. Future missions like the European Space Agency's CMB S4 aim to map these anomalies with unprecedented precision, hunting for the fingerprints of whatever or whoever left the window to reality slightly ajar. Until then, the axis of evil stands as both a cosmic anomaly and an invitation to question, to explore, and perhaps to rewrite the rules we thought we knew. Deep in the direction of the constellations Hydra and Centaurus, something unseen exerts a gravitational pull so immense that it's dragging entire galaxies, including our own Milky Way, toward it at over 14 million miles per hour. Astronomers call this cosmic mystery the Great Attractor, and despite decades of searching, we still don't know exactly what it is, the strangest part. It lies hidden behind the thick dust and stars of our galaxy's disk, cloaked in what astronomers poetically call the zone of avoidance, a region so obscured by interstellar debris that traditional telescopes struggle to pierce through. What makes the Great Attractor so puzzling isn't just its invisibility, it's the scale of its influence. Imagine tossing a handful of leaves into a river and watching them all drift toward the same unseen whirlpool. That's what's happening to galaxies across a mind-boggling stretch of space spanning hundreds of millions of light years. Initially, scientists thought this gravitational behemoth might be the Norma cluster, a dense gathering of galaxies about 250 million light-years away. But the math didn't add up. The Norma cluster, while massive, simply doesn't have enough heft to account for the staggering motion we observe. So what's really out there? One tantalizing possibility is the Laniakea supercluster, a filamentary web of galaxies that includes our own Milky Way. Recent 3D mappings of galactic motions suggest the Great Attractor might be the gravitational center of this colossal structure. a sort of cosmic downtown where the supercluster's mass is most concentrated. Picture Laniakea as a sprawling metropolis with galaxies as commuters flowing toward its densest neighborhoods, yet even this explanation feels incomplete. The pull we're measuring seems to extend beyond Laniakea's borders, hinting at something even larger lurking in the shadows. Then there's the radical idea that the Great Attractor isn't a single object at all, but a ripple in the fabric of space-time, a remnant from the universe's infancy when quantum fluctuations left behind dense knots of dark matter. These knots could form invisible scaffolds, guiding the flow of galaxies like rivers carving canyons over eons. Or perhaps it's something even stranger, a gravitational echo from beyond the observable universe, a structure so vast its shadow stretches into our cosmic neighborhood. Some theorists speculate that our entire local universe might be sliding toward an unfathomably massive concentration of matter, lying just over the horizon of what we can see. The hunt for answers has pushed technology to its limits. Infrared and radio telescopes, like the Parkes Observatory in Australia, have begun peeling back the dusty veil of the zone of avoidance, revealing hints of previously hidden galaxies and clusters. Meanwhile, the European Space Agency's Gaia mission is charting the precise motions of billions of stars, offering new clues about the attractor's gravitational fingerprint. Each discovery adds another piece to the puzzle, but the full picture remains maddeningly out of reach. Here's what makes this mystery so exhilarating. The Great Attractor isn't just pulling galaxies. It's pulling our understanding of the cosmos into uncharted territory. Whether it's a supercluster we've yet to fully map, a dark matter anomaly, or a sign of physics beyond our current models, one thing is certain: the universe still holds colossal surprises hidden in plain sight. And as we inch closer to uncovering them, we're reminded that the deepest cosmic truths often lie not in the light, but in the shadows we're just learning to explore. On a quiet August night in 1977, as most of Ohio slept, a lone astronomer named Jerry Amon sat poring over reams of computer printouts from Ohio State University's Big Ear radio telescope. The data was typically mundane hours of cosmic static punctuated by the occasional blip of a known celestial object. But then his red pen froze over one particular sequence of characters, 6-5. This unassuming string of letters and numbers would become the most tantalizing mystery in SETI history, the WOW signal, a radio burst so perfectly matched to predictions of extraterrestrial communication that Amon couldn't help but circle it and scrawl, "Wow." In the margin, what made this signal extraordinary wasn't its strength, but its specificity. Lasting precisely 72 seconds, the exact duration the Big Ear telescope could observe any fixed point in space, it blared at 1,420 MHz, the emission frequency of neutral hydrogen. Scientists had long proposed this as the universe's natural watering hole, the logical frequency aliens might use to broadcast their presence, since hydrogen is the most abundant element in the cosmos. The signal's intensity followed a near-perfect bell curve, rising and falling as it would if originating from a fixed point beyond our solar system. Yet despite 45 years of searching, we've never heard anything like it again. Theories abound, each more fascinating than the last. Could it have been a comet? In 2017, researchers proposed that two passing comets might have reflected sunlight in just the right way to mimic an artificial transmission. But the math didn't hold. Those comets weren't in the right position in 1977. Others suggest it might have been an intercepted military transmission, though no earthly technology matched the signal's unique profile. Then there's the natural but rare explanation, a previously unknown astrophysical phenomenon, like a neutron star's magnetic hiccup or a rogue black hole's gravitational lensing effect. But the most electrifying possibility remains the one that first crossed Eamon's mind, that for 72 glorious seconds, we weren't alone. The signal originated from the direction of the constellation Sagittarius, where billions of stars host countless potentially habitable planets. If it was intentional, the implications are staggering. A civilization advanced enough to blast a targeted hello across the light years would likely be millennia ahead of us technologically. That they haven't repeated the signal might be deliberate, a cosmic ping, to gauge if anyone's listening before committing to contact. Modern telescopes like the Allen Telescope Array now scan the skies with exponentially more sensitivity than Big Ear, hunting for echoes of that singular event. Meanwhile, new analysis techniques apply machine learning to sift through radio noise for patterns no human could spot. Yet the WOW signal endures as both beacon and enigma, a fleeting cosmic whisper that redefined our place in the universe. Whether it was aliens, astrophysics, or something beyond our current understanding, one truth remains. For one brief moment, the universe asked a question we're still trying to answer. On October 19, 2017, the Pan-STARRS telescope in Hawaii spotted something extraordinary, a faint dot of light hurtling through our solar system at blistering speeds, its trajectory so steep it could only have come from interstellar space. Astronomers named it Oumuamua, Hawaiian for scout or messenger from afar. But this was no ordinary space rock. The more scientists studied it, the stranger it became. First, there was its shape. Unlike typical asteroids or comets, which tend to be roughly spherical or lumpy, Oumuamua appeared elongated, possibly 10 times as long as it was wide, like a cosmic cigar or a pancake tumbling end over end. Then came the real shocker. As it sped away from the sun, it accelerated in ways gravity alone couldn't explain. Comets often speed up slightly due to outgassing, ice turning to vapor and acting like a natural thruster. But Oumuamua showed no visible coma or tail, the telltale signs of such activity. It was as if some unseen force was nudging it along. The scientific community split into two camps. The mainstream explanation, a bizarre but natural object, perhaps a fragment of a Pluto-like world, rich in nitrogen ice that sublimated invisibly, or a porous dust bunny of interstellar debris light enough for sunlight alone to push it. But Harvard astronomer Avi Loeb proposed a more provocative idea. Oumuamua might be artificial, a discarded light sail from an alien civilization. Its unusual acceleration, he argued, matched what we'd expect from a thin, reflective sheet propelled by starlight, a technology humanity is already experimenting with today. The debate raged because Oumuamua vanished before we could get a clear look. By the time telescopes swung toward it, the object was already too distant, leaving us with only fragments of data. Was it a weirdly shaped asteroid, a comet unlike any we'd seen, or something even more extraordinary? The absence of definitive proof became its own kind of Rorschach test, revealing as much about our hopes and biases as about the object itself. What makes Oumuamua so tantalizing isn't just the unanswered questions, it's the possibilities it opens. If it's natural, it suggests interstellar space is littered with exotic objects unlike anything in our solar system, remnants of planetary systems built under alien suns. If it's artificial, even partially, it implies we're not just scanning the cosmos for life. We might have already brushed shoulders with its artifacts. Future telescopes like the Vera Rubin Observatory will scan the skies for more visitors like Oumuamua, ready to capture them before they slip away. Until then, this mysterious scout remains a cosmic riddle, a fleeting whisper from the vast unknown, one that challenges us to keep looking up and to wonder what else might be sailing silently through the dark. For decades, amateur radio operators and conspiracy theorists have claimed something unnatural circles our planet, not the International Space Station or weather satellites, but a mysterious object dubbed the Black Knight. Purported to be an alien probe or ancient artificial satellite predating human spaceflight, this enigmatic visitor has sparked debates that blur the line between cosmic mystery and urban legend. The story begins with strange radio signals. In the late 19th century, Nikola Tesla reported intercepting repetitive pulses he believed originated from beyond Earth, a claim later echoed in the 1920s by Norwegian engineers studying long-delayed radio echoes. Fast forward to 1960, when Time magazine reported the U.S. Navy had detected a dark object in polar orbit, a trajectory unusual for human-made satellites at the time. These fragments of history fused into modern myth, an extraterrestrial satellite silently observing us for centuries, perhaps millennia. But here's where skepticism takes the wheel. The Black Knight likely isn't a single object but a collage of misidentified phenomena. One prime candidate: thermal blankets lost during a 1998 space shuttle mission, which tumbled in orbit, reflecting sunlight in erratic patterns. Another possibility: the debris field from early satellite launches, like the 1958 Discoverer missions, whose discarded rocket stages still haunt low Earth orbit. Even Tesla's signals could have been pulsars, neutron stars emitting regular radio bursts decades before their official discovery. Yet the allure persists, fueled by grainy NASA photographs and whispered accounts of astronauts spotting unexplained objects during spacewalks. Some theorists point to the object's alleged 13,000-year orbit, a number plucked from speculative archaeology, as proof of ancient alien technology. Scientists counter that no stable orbit lasts millennia without decay. Even the pyramids would have seen this satellite vanish into atmospheric drag long ago. The truth: space is cluttered with humanity's discarded hardware, over 9,000 tons of it, and the Black Knight is probably just another piece of cosmic scrap. But its legend endures because it taps into a deeper question. If aliens were monitoring Earth, wouldn't they leave something behind? In that sense, the Black Knight isn't just debris, it's a mirror, reflecting our timeless hope that we're not alone in the universe and that the stars might be watching back. Every evening, just after sunset or right before dawn, if the conditions are just right, you might catch a glimpse of something ethereal, a faint, pyramid-shaped glow stretching upward from the horizon. This isn't the Milky Way or light pollution, it's the Zodiacal light, a celestial phenomenon caused by sunlight scattering off trillions of dust particles drifting through the inner solar system. But here's the mystery: these particles shouldn't be there. Conventional wisdom says this dust ought to have vanished eons ago. The solar wind, a relentless stream of charged particles from the sun, should have swept it away. Jupiter's gravity, the solar system's vacuum cleaner, should have flung it into interstellar space, yet the dust persists, glowing like a cosmic campfire in the darkness. So where is it coming from? One leading theory points to comets. As these icy wanderers swing close to the sun, they shed debris in their tails, leaving behind trails of dust like breadcrumbs. Asteroids colliding in the belt between Mars and Jupiter might also contribute, grinding each other down into fine powder over millions of years. But calculations suggest these sources can't fully account for the sheer volume of dust we observe. There's too much of it, too evenly distributed, as if something or someone is constantly replenishing the supply. Then there's the wild card: interstellar interlopers. Tiny grains of dust from beyond our solar system, drifting in on the galactic breeze, could be mixing with local material. Some researchers even speculate about more exotic origins, like the remnants of a long-vanished planet or debris from a primordial collision that's been circling the sun undetected for billions of years. But the plot thickens when you examine the dust itself. Unlike the rough, irregular particles you'd expect from asteroid collisions, zodiacal dust is oddly smooth, almost polished. One possible explanation: the relentless bombardment of solar radiation has sculpted these grains over time, sanding them down to microscopic perfection. Another idea suggests they're coated with organic molecules, giving them a glossy sheen that reflects sunlight more efficiently. The most tantalizing clue, though, comes from the way the dust moves. Instead of dispersing randomly, it clusters in faint bands and arcs, hinting at hidden gravitational influences, perhaps undiscovered asteroids or even the gravitational echoes of ancient planetary migrations. Future missions like Japan's Destiny Plus probe aim to fly through these dust clouds, analyzing their composition in situ. What they find could rewrite our understanding of the solar system's hidden architecture. So the next time you see that ghostly glow on the horizon, remember, you're not just looking at dust, you're witnessing a cosmic crime scene, a puzzle that's lingered since the birth of the planets, one that's still waiting for its detective to crack the case. In the vast emptiness between planets, where gravity's grip should be predictable and unchanging, two robotic pioneers began drifting off course. Pioneer 10 and 11, launched in the early 1970s to explore the outer solar system, were expected to glide through space with near-perfect precision. Yet as they hurtled toward the stars, something peculiar happened. Both spacecraft slowed down slightly, just a fraction more than physics predicted, as if an invisible hand had reached out to gently tug them backward. This tiny discrepancy, barely noticeable at first, ballooned into one of the most stubborn mysteries in modern astrophysics, the Pioneer Anomaly. At first, scientists assumed the answer would be mundane. Spacecraft are complex machines, after all. Maybe a fuel leak was producing unseen thrust. Perhaps sunlight bouncing off the probe's antennas was nudging them off course. Even the faintest pressure from escaping heat could, over decades, add up to a measurable drift. But as researchers crunched the numbers, none of these explanations fully accounted for the anomaly. The deceleration was too consistent, too uniform, as if some unseen force was at work, acting equally on both spacecraft across billions of miles. This consistency sparked wilder theories. Could it be evidence of dark matter's gravitational pull, clustering in ways we don't yet understand, or a flaw in Einstein's theory of general relativity, revealing itself only in the vast, uncharted distances between planets? Some physicists even floated the idea of modified inertia, a tweak to Newton's laws that would explain the slowdown without invoking invisible matter or new physics. The most tantalizing and controversial suggestion was that the anomaly hinted at extra dimensions, their unseen geometry subtly altering how gravity behaves over cosmic scales. Then, in 2012, the plot thickened. A painstaking analysis of decades-old engineering data revealed a likely culprit: heat, not from the sun or external forces, but from the probe's own radioactive power sources. As the plutonium in their generators decayed, it emitted warmth that radiated unevenly off the spacecraft surfaces. This thermal recoil, though infinitesimally small, could have provided just enough push to account for the anomaly. Case closed, not quite. While the heat theory fits much of the data, some researchers argue it doesn't fully explain the probe's trajectories. The debate lingers, a testament to how even the tiniest discrepancies can unravel our assumptions about the cosmos. What makes the Pioneer Anomaly so compelling isn't just the mystery itself, it's what it represents. In science, anomalies are more than errors, they're opportunities. They force us to question what we think we know, to dig deeper into the fabric of reality. Whether the solution lies in overlooked engineering details or undiscovered physics, one thing is certain: the universe still holds surprises, even in the quiet drift of machines we built half a century ago. And sometimes it's the smallest deviations that point us toward the biggest truths. Beyond the frozen reaches of Neptune, where sunlight is 1,000 times dimmer than on Earth, astronomers have stumbled upon a cosmic conundrum, a boundary so abrupt it's as if someone drew a line in the celestial sand. This is the Kuiper Cliff, a region where the expected population of icy objects plunges to near zero, defying every model of how solar systems form. It's not just a gradual thinning like a trail fading into the wilderness. It's a hard stop, as if an invisible bouncer stands guard at the edge of our solar system, turning away comets and dwarf planets with a gravitational no-entry sign. The textbook explanation for our solar system structure involves the gentle decay of debris as you move outward, more scattered but still present. Yet when telescopes like Pan-STARRS and the Subaru telescope mapped the Kuiper belt, they found a stark cutoff roughly 50 astronomical units from the Sun, 1.0 being the distance from Earth to the Sun. Beyond this point, the number of detectable objects drops by 99%. It's as if you were walking through a forest and suddenly stepped into a barren desert with no transition, no warning. So what's lurking out there? One tantalizing possibility is Planet 9, a hypothetical world up to 10 times the mass of Earth, orbiting hundreds of O away. Its gravity could act like a cosmic broom, sweeping the outer Kuiper belt clean of debris. The math supports this. Simulations show a distant, massive planet could herd objects into clustered orbits while ejecting others into the void. But here's the catch: despite years of searching, no telescope has spotted this elusive world. Some argue it could be a primordial black hole, a grapefruit-sized singularity left over from the Big Bang, its gravity warping space without emitting light. Others suggest it might not be one object at all, but a swarm of smaller, unseen bodies collectively sculpting the cliff. Then there's the radical alternative. Our models of solar system formation are fundamentally flawed. Maybe the Kuiper Cliff marks the edge of the Sun's primordial birth cloud, a fossilized boundary from the nebula that birthed our planets. Or perhaps the outer solar system was stripped bare by a close encounter with another star in our Sun's youth, a stellar thief that stole our icy debris billions of years ago. The implications stretch beyond astronomy. If Planet 9 exists, its discovery would rewrite our understanding of the solar system's architecture. If it doesn't, the Kuiper Cliff becomes a glaring anomaly, forcing us to reconsider how planetary systems evolve. Every new survey, like the upcoming Vera Rubin Observatory's decade-long scan of the sky, brings us closer to an answer. So while the Kuiper Cliff might seem like a distant curiosity, it's really a cosmic detective story, one where the clues are written in ice and shadow. And the solution, whatever it may be, promises to reveal secrets not just about our backyard, but about how all solar systems dance on the edge of chaos and order. The moon hangs in our night sky as a silent, cratered companion barren, airless and seemingly frozen in time. But 4 billion years ago, it may have harbored a secret that defies everything we know about planetary physics, a magnetic field. Today, moon rocks collected during the Apollo missions bear traces of this ancient force, their minerals magnetized as if influenced by a powerful dynamo. Here's the puzzle. Earth's magnetic field comes from its churning molten core, a spinning engine of liquid iron. The moon, though, its core is far too small and inactive to have generated such a field. So what cosmic sleight of hand could have temporarily turned our moon into a magnet? One theory points to a primordial dance of destruction. In the moon's infancy, its orbit was much closer to Earth, and tidal forces, the same gravitational tug that creates ocean tides, may have stretched and squeezed its core like putty. This relentless flexing could have heated the moon's interior, stirring its metals into a temporary frenzy capable of generating magnetism. Picture a ball of molten iron being kneaded by invisible hands, its motion creating electric currents that birthed a magnetic field. But there's a catch. Simulations suggest this effect would have faded within a few 100 million years, yet some moon rocks hint at magnetism lasting far longer. Another possibility is even more dramatic. Massive asteroid impacts during the moon's violent early history might have supercharged its core. When a city-sized rock slammed into the lunar surface, the shockwaves could have sent tsunamis of molten rock rippling through its mantle, briefly jump-starting a magnetic dynamo. Think of it like striking a bell. The impact rings through the moon's interior, creating waves of motion that electrify its core. Some scientists speculate these collisions weren't just one-time events, but a series of celestial hammer blows, each reawakening the moon's magnetic field like a battery being repeatedly recharged. Then there's the wild card, crystallization. As the moon's magma ocean cooled, dense minerals like ilmenite may have sunk toward the core, displacing lighter material upward in a process called core overturn. This churn could have created just enough movement in the moon's metals to spark magnetism like a spoon stirring a cup of coffee, but on a planetary scale. The key difference: this spoon moves once, then stops, leaving behind a fading ripple of magnetic energy. But the most tantalizing clue lies in the rocks themselves. Certain lunar samples show magnetism that doesn't align with the moon's current orientation, suggesting its magnetic poles once wandered freely, even flipping entirely. This bizarre behavior hints at a dynamo unlike Earth's, one driven by short-lived, chaotic forces rather than a stable, spinning core. It's as if the moon's magnetic field was a flickering candle, flaring brightly one moment and guttering the next, powered by mechanisms we've yet to fully unravel. What makes this mystery so compelling isn't just the moon's past, it's what it reveals about other worlds. If a small, geologically dead body like the moon once hosted a magnetic field, could the same be true for exoplanets we've written off as inert? Magnetic fields shield planets from solar radiation, preserving atmospheres and potentially fostering life. The moon's hidden history suggests magnetism might be more versatile, more ephemeral than we ever imagined. So the next time you gaze up at that familiar gray orb, remember, its quiet surface hides the echoes of an ancient powerhouse, a time when the moon wasn't just a reflector of sunlight, but a player in the cosmic game of forces. And somewhere in those Apollo-era rocks, the secret to its lost magnetism waits not just as a lunar curiosity, but as a clue to how planets, both here and beyond, protect themselves in the darkness of space. Venus is a world of extremes, a blistering, toxic hellscape with surface temperatures hot enough to melt lead and atmospheric pressures that would crush a submarine. But high above its scorching plains at the planet's north pole, something even stranger spins in the perpetual gloom. A colossal double vortex, a pair of intertwined storms raging in perfect synchrony. This isn't just another planetary storm. It defies every rule we know about atmospheric behavior, twisting and reshaping itself with a rhythm that feels almost alive. What makes this vortex so bizarre? For starters, its shape. Unlike Earth's polar cyclones, which spiral inward like water draining from a bathtub, Venus's vortex forms a distinct figure-8 pattern, two connected funnels rotating around each other like celestial dancers. Infrared observations reveal the structure morphing constantly, sometimes stretching into an elongated hourglass, other times collapsing into a tight, writhing knot. The storm's speed is equally erratic, with winds whipping at nearly 200 miles per hour before abruptly slowing, as if the vortex itself is breathing. Theories abound, but none fully explain this atmospheric oddity. One leading idea points to Venus's superrotation. Its atmosphere spins 60 times faster than the planet itself, a phenomenon unmatched in the solar system. This relentless motion might generate standing waves of air that converge at the poles, forcing gases into these swirling formations. Another possibility involves the planet's thick blanket of sulfuric acid clouds. Sunlight heats these clouds unevenly, creating turbulent updrafts that could twist into self-sustaining vortices. But why two? Why not one or a dozen? Then there's the wild card, Venus's lack of a magnetic field. Without this protective shield, solar wind particles slam into the upper atmosphere, potentially injecting energy that destabilizes the vortex in ways we don't yet understand. Some researchers even speculate that the double vortex acts like a planetary pressure valve, redistributing heat from the sun-baked equator to the frigid poles in a desperate attempt to balance the planet's crushing climate. The most tantalizing clue might lie in the vortex's heartbeat like pulses. Every few Earth days, the structure contracts and expands with eerie regularity, as if responding to some hidden cosmic metronome. Could this be the fingerprint of an undiscovered fluid dynamic, a quirk of physics that only manifests under Venus's extreme conditions? Or is it evidence of deeper, unseen forces like underground volcanism pumping gases into the atmosphere, or even interactions with the solar wind we've yet to map? Every probe sent to Venus from the Soviet Venera missions to ESA's Venus Express has returned more questions than answers. But one thing is certain: this swirling enigma isn't just a curiosity. It's a window into the chaotic ballet of planetary atmospheres, a reminder that even in our own cosmic backyard, the universe still holds mysteries that defy our textbooks. And until we land a spacecraft in that roiling maelstrom, the Venusian vortex will keep spinning, whispering its secrets just out of reach. Mars should be a dead world, frozen, barren, and chemically inert. Yet something on the red planet is breathing. Since 2003, orbiters and rovers have detected sporadic plumes of methane gas, a compound that on Earth is overwhelmingly produced by living organisms. These aren't steady leaks either. The methane appears in sudden bursts, sometimes vanishing within weeks, as if Mars itself is playing a cosmic game of hide and seek with its most tantalizing secret. At first glance, methane shouldn't survive long in the Martian atmosphere. Solar radiation and chemical reactions should break it apart within a few hundred years. So when NASA Curiosity rover measured methane levels spiking tenfold in just 60 Martian days, scientists were left scrambling for explanations. Where is this gas coming from? And why does it vanish so abruptly? The biological angle is irresistible. On Earth, over 90% of atmospheric methane comes from microbes or other living sources. Could subsurface bacteria be thriving in Mars's icy aquifers, releasing gas through cracks in the bedrock? Some extremophiles on Earth survive in similar conditions, buried deep in permafrost or hydrothermal vents. If life exists on Mars today, methane would be its most likely calling card, a microscopic shout across the void. But geology has its own compelling case. Serpentinization, a chemical reaction between water and certain minerals like olivine, can produce methane without any biology involved. Mars's crust is rich in these very minerals, and underground water reservoirs might still linger beneath the surface. Even more dramatic, methane could be trapped in ancient clathrates ice like cages of frozen gas, slowly destabilizing due to seasonal temperature shifts or meteor impacts. releasing sudden puffs into the atmosphere like a planetary pressure cooker venting steam. Then there's the wild card, dust. Some researchers argue that ultraviolet light interacting with wind-blown organic dust could generate methane through photochemical reactions. It's a tidy explanation, except Curiosity's measurements show methane levels rise at night precisely when UV light is absent. If dust isn't the culprit, could electrostatic charges from Martian dust storms be triggering methane release from the soil? The plot thickens when you compare orbital and ground-level data. ESA's Trace Gas Orbiter, designed specifically to sniff out methane from above, has repeatedly failed to confirm Curiosity's detections. This discrepancy might hint at something even stranger: localized near-surface sources. Imagine methane seeping from a single underground pocket, dispersing too quickly to be seen from orbit, like a steam vent in Yellowstone, invisible beyond its immediate plume. Every new observation deepens the mystery. In 2019, Curiosity recorded its largest spike yet, 21 parts per billion, the highest concentration ever measured. Yet weeks later, the gas was gone without a trace. If life is producing these bursts, why isn't it constant? If geology is to blame, why don't other gases like hydrogen sulfide appear alongside it? The answer might lie in Mars's subsurface, a hidden realm we've barely begun to explore. Future missions like NASA's Mars Life Explorer, designed to drill deeper than ever before, could finally settle the debate. Until then, Mars keeps whispering its methane riddles, daring us to distinguish between the echoes of a long-dead world and the faint, hopeful pulse of something still alive. Saturn's moon Titan is a world of eerie familiarity, a place where rivers carve valleys into icy bedrock, where rain falls from thick clouds, and where vast seas stretch across the landscape. But this isn't water. Titan's hydrologic cycle runs on methane, a liquid that behaves nothing like the oceans we know. These alien lakes and seas ripple with waves that defy earthly logic, moving sluggishly as if weighed down by invisible hands. The physics here aren't just different, they're rewriting the rules of fluid dynamics right before our eyes. Take Titan's largest sea, Kraken Mare, spanning over 400,000 square kilometers, larger than Earth's Caspian Sea. It's a sprawling expanse of liquid methane and ethane. Yet when NASA Cassini spacecraft observed it, the surface appeared unnervingly smooth. No crashing breakers, no whitecaps, just glassy stillness broken occasionally by faint ripples no taller than a few centimeters. On Earth, even the calmest lakes stir under gentle breezes. So why does Titan's liquid barely budge? The answer lies in the Moon's bizarre cocktail of conditions. Titan's gravity is just 1/7 of Earth's, meaning waves struggle to gain momentum. Its thick atmosphere, 4 times denser than ours, damps wind speeds near the surface, preventing the gusts needed to churn up larger swells. And then there's the methane itself. Unlike water, which has strong surface tension, liquid methane is far slipperier, making it harder for waves to form cohesive peaks. But the real mystery isn't the absence of waves, it's their inconsistency. Radar images have caught fleeting glimpses of what scientists call phantom waves, sudden disturbances that appear and vanish without explanation. Some researchers suspect these could be caused by methane bubbles rising from the seafloor, belching gases trapped beneath. Others propose they're the result of tidal forces from Saturn's gravity, subtly flexing Titan's crust and sloshing its seas in ways we can't yet model. There's even a wilder possibility that these lakes aren't pure methane at all, but a complex slurry of organic compounds, a sort of cosmic petroleum that changes viscosity with temperature, creating unpredictable pockets of thick and thin liquid. Then there's Titan's shorelines. On Earth, waves and currents sculpt coasts into smooth curves or jagged cliffs. Titan's coastlines, though, are something else entirely. Some regions show sharp, angular boundaries, as if the liquid is eating away at the ice in precise geometric patterns. Others have porous, sponge-like edges, riddled with channels that seem to drain the seas from below. This isn't erosion as we know it, it's dissolution, a slow-motion melting where methane chemically interacts with water ice, carving labyrinths beneath the surface. The most tantalizing question of all, whether these methane seas could harbor life, not as we know it but as we don't. On Earth, extremophiles thrive in boiling vents and acid pools. On Titan, where temperatures hover around -180 degrees Celsius, any life would need to operate in liquid methane instead of water. It's a radical idea, but some scientists speculate that cell membranes could form from acrylonitrile, a molecule detected in Titan's atmosphere, creating structures stable enough to function in these frigid, alien seas. As we peer through Titan's haze, one thing becomes clear: this isn't just another moon. It's a laboratory for fluid dynamics unlike anything in our solar system, a place where the most basic assumptions about liquids and landforms are turned inside out. And with NASA, a Dragonfly mission set to explore Titan's surface in the next decade, we might finally get a front-row seat to watch these methane waves roll in, or discover they're not waves at all, but something far stranger. Beneath Europa's frozen crust, an ocean twice the volume of Earth's sloshes in perpetual darkness, locked away under miles of ice so thick it could bury mountains. But every so often, this hidden sea breaks free, erupting into space in towering geysers that scatter water vapor and ice crystals across the void. These aren't just random spurts. They're direct samples from a liquid abyss that might have persisted for billions of years, untouched by sunlight but possibly teeming with life. The first hints of these plumes came in 2012, when the Hubble Space Telescope caught ultraviolet glimpses of what appeared to be water vapor near Europa's south pole. Unlike the predictable cryovolcanoes of Enceladus, Europa's eruptions are erratic, sometimes vanishing for years before flaring up again. Their unpredictability suggests something profound. This moon's icy shell isn't just a static lid. It's a dynamic, shifting landscape where tidal forces from Jupiter's gravity flex and fracture the ice, creating temporary conduits for the ocean below to vent its secrets into space. What makes these plumes so tantalizing isn't just the water, it's what might be riding along with it. On Earth, hydrothermal vents at the bottom of the ocean sustain entire ecosystems without a single photon of sunlight. Europa's seafloor, heated by the same tidal kneading that cracks its surface, could host similar vents, pumping out minerals and organic compounds. If life exists there, even in microbial form, traces of its chemistry, perhaps amino acids or lipids, could be frozen into the plume's icy particles, waiting to be scooped up by a passing spacecraft. The logistics of catching these samples are as tricky as they are thrilling. Europa's plumes don't behave like Enceladus's steady jets. They're more like sneezes, brief, localized, and unpredictable. NASA's upcoming Europa Clipper mission, set to launch in 2024, will orbit Jupiter and make dozens of close flybys, armed with instruments designed to sniff and analyze plume material on the fly. But the real challenge lies in distinguishing between biological signatures and false alarms. Salt from the ocean could mimic the spectral fingerprints of certain organics, while radiation from Jupiter's magnetic field might break down complex molecules into misleading fragments. Then there's the question of energy. Life needs more than water and chemicals, it needs a power source. On Earth, hydrothermal vents provide both heat and chemical gradients that microbes exploit. Europa's ocean, cut off from sunlight, would rely entirely on such geothermal activity. But how widespread are these vents? Are they concentrated near the poles where the ice is thinnest, or scattered across the seafloor like a string of underwater volcanoes? The plumes might hold clues. Variations in their composition could map hidden heat sources below, like steam rising from cracks in a frozen lake pointing to warm currents beneath. But Europa's plumes aren't just scientific targets, they're ethical dilemmas. If we detect signs of life, how do we proceed? A lander drilling through the ice could contaminate the very ecosystem we're trying to study. Even a flyby risks introducing earthly microbes that might hitch a ride on spacecraft. NASA and other space agencies have strict planetary protection protocols, but Europa's plumes add a new wrinkle. They're both a gift and a warning, offering easy access to the ocean while reminding us of the stakes. The most haunting possibility: the plumes might be fleeting. Europa's surface is young, geologically speaking, constantly resurfaced by new ice. If the ocean's vents clog or shift over time, the geysers could shut off, locking away their secrets for good. That's what makes this moment so urgent. We're not just studying a moon, we're racing against cosmic time, chasing whispers from an ocean that's been waiting 4.5 billion years to speak. So when Europa Clipper skims through those icy plumes in the coming decade, it won't just be collecting data. It'll be fishing in the darkest waters of our solar system, dangling a line into the unknown, and what it reels in could change everything we think we know about life's boundaries. In 2015, astronomers studying data from the Kepler Space Telescope stumbled upon a star that defied all expectations. KIC 8,462,852, better known as Tabby's star after astrophysicist Tabitha Boyajian. Unlike ordinary stars that dim and brighten in predictable rhythms, this one flickered like a candle in the wind, plunging in brightness by up to 22% at irregular intervals. The dips weren't just dramatic, they were chaotic, lasting days or weeks with no discernible pattern. For comparison, when a planet transits a star, it typically blocks less than 1% of the light. Whatever was casting shadows across Tabby's star wasn't just big, it was utterly unlike anything we'd seen before. Theories erupted like solar flares. At first, scientists suspected a colossal cloud of comets, shattered remnants of some cosmic collision drifting in front of the star, but the math didn't add up. To dim the star that severely, you'd need a swarm of millions of giant comets, an implausible scenario even for the most chaotic stellar systems. Then came the jaw-dropping alternative: alien megastructures. Specifically, a Dyson swarm, a hypothetical array of energy-collecting satellites or panels encircling the star, built by an advanced civilization to harvest its power. The irregular dimming could be explained by massive construction projects in progress, with panels shifting in and out of view. It was a wild idea, but for a brief moment, science flirted with the possibility that we might have spotted the fingerprints of extraterrestrial engineers. Of course, extraordinary claims demand extraordinary evidence. Follow-up observations revealed another clue: the dimming wasn't uniform across all wavelengths. Light at shorter wavelengths, bluer light, was blocked more than red light. That's a telltale sign of dust, not solid megastructures. Dust particles scatter blue light more effectively, much like Earth's atmosphere makes the sky appear blue. By 2018, the evidence tilted decisively toward a natural explanation: vast, uneven clouds of fine-grained cosmic dust, possibly from a disintegrating moon or a recent planetary collision. Yet even this answer left gaps. Why was the dust distributed so unevenly? And why did the star's long-term brightness show a gradual, century-long decline, as if something far larger was slowly encroaching? The most compelling data came from the star's own behavior. In 2017, Tabby's star dimmed again, and astronomers worldwide trained their telescopes on it. This time, they caught the culprit in action. Spectral analysis confirmed the presence of dust, but with a twist. The particles weren't just passing by. They seemed to be part of a complex, dynamic system, perhaps a massive ringed planet in the process of breaking apart, or a protoplanetary disk in chaotic disarray. Some researchers even proposed a captured interstellar object, a rogue body from another star system, now unraveling as it orbits too close to Tabby's fiery embrace. But here's why Tabby's star still captivates. It's a reminder of how much we don't know. Even if dust is the primary actor, the sheer scale and irregularity of these clouds challenge our models of stellar environments. Most stars don't behave this way, so what makes this one so different? Is it a rare glimpse of planetary demolition in real time, or could there still be room for exotic explanations, like naturally occurring megastructures of a different kind, perhaps dense asteroid belts or exotic magnetic fields bending light in ways we've yet to understand? The legacy of Tabby's star isn't just about solving a single cosmic whodunit. It's about the thrill of the unknown, the questions that push us to build better telescopes, refine our models, and stay open to possibilities that once seemed like science fiction. Because sometimes the universe's strangest anomalies aren't just puzzles to solve, they're invitations to rethink what's possible. And as long as stars like this keep winking at us from the void, we'll keep watching, wondering, and searching for the next clue in the great cosmic mystery. At the outer edges of our Milky Way, where stars thin to a scattering and the glow of galactic civilization fades, something strange lingers in the darkness, not just emptiness, but an invisible boundary humming with energy. Star Trek fans might recognize this as the galactic barrier, that shimmering cosmic wall the Enterprise battled in classic episodes, but fiction might be closer to reality than we thought. Astronomers have detected peculiar energetic signatures at the fringes of galaxies, regions where the rules of physics seem to shift and particles behave in ways that defy expectations. These aren't literal walls, of course, but they might be something just as intriguing, the fingerprints of forces we've yet to fully understand. So what sculpts these cosmic borders? One leading theory points to dark matter, the invisible scaffolding of the universe. At a galaxy's edge, the density of dark matter drops sharply, creating a sort of gravitational shoreline where normal matter, like stars and gas, meets the void. This transition zone could generate shock waves, similar to how ocean waves crash against a beach, energizing particles and producing faint but detectable radiation. Another possibility involves magnetic fields. Galaxies are threaded with colossal magnetic filaments, and at their outer limits, these fields might tangle and amplify, creating a kind of electromagnetic fence that traps high-energy particles. Picture a celestial version of Earth's Van Allen belts, but on a scale so vast it could take light thousands of years to cross. Then there's the wild card, cosmic rays. These high-speed particles, blasted across the universe by supernova and black holes, might pile up at galactic edges like snow against a fence. As they collide with the thin gas lingering there, they could produce bursts of gamma rays or X-rays, a faint, crackling glow marking the boundary between a galaxy and the intergalactic wilderness. Some researchers even speculate that these barriers aren't static. They could pulse and ripple over time, shaped by the galaxy's rotation or collisions with nearby cosmic structures. But the most tantalizing idea, these edges might be more than just physical boundaries. They could be cosmic filters, regions where the fundamental laws of physics subtly shift. Certain theories of modified gravity, like MUND, suggest gravity behaves differently at the outskirts of galaxies, where matter thins out. If true, the galactic barrier might be a laboratory for exotic physics, a place where our understanding of reality gets stretched to its limits. So while we may never see a glowing purple wall like in Star Trek, the truth might be just as wondrous. These invisible frontiers remind us that galaxies aren't just floating islands in space, they're dynamic, evolving entities with edges that crackle with hidden energy. And as we peer deeper into these mysterious zones, we're not just mapping the boundaries of our galaxy, we're testing the boundaries of our knowledge. The universe keeps meticulous ledgers, every atom, every particle accounted for in the grand equations of cosmology. But somewhere between the Big Bang's fiery birth and today, the cosmos misplaced something critical: lithium. According to our best models, there should be 3 times more of this lightweight metal floating between the stars than what telescopes actually detect. It's not just a rounding error, it's a glaring discrepancy that's had astrophysicists scratching their heads for decades. Where did all that lithium go? Was it swallowed by stars, dissolved by dark matter, or is there a fundamental flaw in how we understand the universe's earliest moments? Let's rewind to the first few minutes after the Big Bang, a period called nucleosynthesis. Here, in a searing plasma of protons and neutrons, the universe forged its first atomic nuclei, mostly hydrogen and helium, with trace amounts of lithium and beryllium. The math is precise. For every billion hydrogen atoms, there should be about 100 lithium atoms. Yet when astronomers measure lithium abundances in ancient stars, the cosmic time capsules that preserve primordial chemistry, they find only 30 or so per billion. That's like baking a cake with a cup of sugar but tasting only a third of it. The rest has vanished without a trace. One tantalizing explanation lies inside stars themselves. Lithium is fragile, easily destroyed in nuclear reactions at temperatures above 2 million degrees, a mere sauna by stellar standards. Some theories suggest that as lithium-rich gas collapsed into the first stars, convection currents dragged it into scorching inner layers where it was incinerated. Picture a snowflake falling into a volcano, gone before it even had a chance to land. But here's the catch. While this might explain lithium depletion in some stars, others, like red dwarfs, have cool enough exteriors to preserve the element. Yet even their outer atmospheres show the same lithium deficit. If stars aren't the culprits, what is? Enter the exotic possibilities. Could actions hypothetical particles of dark matter be interacting with lithium nuclei, subtly transmuting them into other elements? Or might primordial black holes, those grapefruit-sized singularities left over from the Big Bang, have swallowed lithium-rich clouds in the universe's chaotic infancy? There's even a wild card. Quantum gravity effects in the early universe might have altered nuclear reaction rates, skewing lithium production from the start. Each theory dances on the edge of known physics, hinting at realms we've yet to explore. But the most unsettling answer might be the simplest: we've miscalculated. The standard model of nucleosynthesis relies on precise measurements of nuclear cross-sections, the probabilities of atomic interactions. What if these values are slightly off? Recent lab experiments suggest certain nuclear reactions involving beryllium-7, a lithium precursor, might proceed faster or slower than previously thought. A tiny tweak here could cascade into a lithium shortfall. It's like realizing your baking recipe was wrong all along, not because the sugar disappeared, but because you misread the scale. The stakes are higher than just solving a cosmic accounting error. Lithium is a litmus test for our understanding of the universe's first moments. If new physics is at play, whether exotic particles or hidden dimensions, it could rewrite textbooks. On the other hand, if the issue lies in nuclear measurements, it's a humbling reminder that even our most trusted models are built on shifting sands. As next-generation telescopes like the Extremely Large Telescope begin analyzing starlight with unprecedented precision, we're not just hunting for missing atoms. We're interrogating the universe's ledger, searching for clues that might reveal whether the error lies in our math or in the fabric of reality itself. And somewhere in that discrepancy between prediction and observation lies a crack in our understanding waiting to be pried open. From quantum quirks to galactic oddities, these 42 unconventional approaches peel back the curtain on a universe that defies every expectation. Imagine a reality where particles communicate instantaneously across cosmic distances, where black holes might encode the universe's deepest secrets like celestial librarians, and where the fabric of space-time itself could be a holographic projection. This isn't science fiction, it's the frontier of human understanding, a testament to how much we've yet to discover. What makes these mysteries so exhilarating isn't just their strangeness, but what they reveal about our place in the cosmos. For centuries, we've mapped the heavens with ever-growing precision, only to find that the closer we look, the more the universe surprises us. Dark matter tugs at galaxies with invisible fingers. Quantum fluctuations birth particles from empty space. Even time, that most familiar of dimensions, bends and warps under extreme conditions. These aren't flaws in nature's design, they're invitations to dig deeper, to question the assumptions we've long taken for granted. Think of it like standing at the edge of an uncharted ocean. The waves we've studied, the tides we've measured, they're just the surface. Beneath lies a world of hidden currents, unexplored trenches, and creatures unlike anything we've imagined. Every anomaly, every paradox is a clue, a ripple pointing to something grander. The Fermi bubbles towering over our galaxy, the eerie synchrony of the zodiacal light, the lithium deficit whispering of physics beyond our models, they're not roadblocks. They're signposts urging us forward, and here's the most thrilling part. This journey isn't just for physicists in labs or astronomers at telescopes. It's for anyone who's ever looked up at the night sky and wondered. Maybe you're captivated by the idea of parallel universes brushing against our own, or the possibility that consciousness itself might shape reality. Perhaps the notion of cosmic strings cracks in the universe's foundation sets your mind racing. Whatever sparks your curiosity, these ideas remind us that the universe isn't a static backdrop. It's a living puzzle, one we're all piecing together. So what's next? The answers won't come easily, but the hunt is half the magic. New telescopes peer deeper into space, quantum computers simulate alternate realities, and labs recreate conditions from the dawn of time. Every breakthrough, every dead end, every aha moment adds another stitch to the tapestry of understanding. And you're part of this story too. Whether you're debating the nature of dark energy or marveling at the enigma of Tabby's star, you're keeping the spirit of exploration alive. The universe's greatest secret might be that it never runs out of surprises. So keep questioning, keep dreaming, and above all, stay curious. The next cosmic revelation could be just one observation away, waiting for someone like you to connect the dots. After all, the stars don't just shine above us, they invite us to join the conversation. Imagine a telescope so powerful it could analyze 1 billion galaxies in a single night, or a cosmic detective that pours through centuries of data in seconds, spotting patterns no human eye could ever catch. This isn't science fiction, it's the reality of artificial intelligence in modern astronomy, where machine learning algorithms are transforming how we unravel the universe's deepest secrets. From mapping the invisible scaffolding of dark matter to predicting the violent dance of colliding neutron stars, AI isn't just assisting scientists, it's reshaping the very fabric of discovery. Take black holes, for instance. Simulating these cosmic monsters requires crunching equations so complex they'd take supercomputers months to solve, but AI shortcuts this process dramatically. Neural networks trained on known physics can now approximate black hole behavior in hours, generating shockingly accurate models of how they warp space-time or devour stars. In 2019, the Event Horizon Telescope collaboration used machine learning to sharpen the first ever image of a black hole's shadow, filling in gaps caused by missing data like a cosmic sketch artist. The result, a clearer glimpse of M87's monstrous core than traditional methods could achieve. Then there's the data deluge. Modern observatories like the Vera Rubin telescope will generate terabytes of images nightly, far more than human teams could ever analyze. AI thrives in this chaos. Algorithms trained to recognize galactic shapes, stellar explosions, or even subtle light distortions from gravitational lenses act as tireless assistants, flagging anomalies for closer inspection. Already, machine learning has spotted dozens of previously overlooked asteroids in archival sky surveys, and even identified rare, fast radio bursts, mysterious cosmic radio pulses buried in noise that would have stumped human researchers. But the most exciting frontier lies in AI's ability to dream up entirely new hypotheses. Unlike traditional software, which follows predefined rules, advanced neural networks can detect correlations in data that defy conventional theories. At Stanford, researchers fed an AI simulations of the universe's structure and watched as it independently discovered the concept of dark matter, not by being taught, but by inferring that visible matter alone couldn't explain galactic motions. Similarly, Google's DeepMind has designed AI that predicts the movement of celestial bodies with 10 times the accuracy of classical methods, hinting at uncharted physics hidden in Newton's old equations. Of course, AI isn't a magic wand. Its greatest strength finding patterns can also be its weakness when those patterns are mirages. In 2021, an algorithm scanning Kepler Space Telescope data flagged a star with an 85% chance of hosting an alien megastructure. Excitement flared until follow-up observations revealed a more mundane culprit: instrumental artifacts. The lesson: AI excels at proposing answers, but human intuition remains essential for interpreting them. Yet the potential is staggering. Future AI might decode quantum fluctuations in the cosmic microwave background, uncovering traces of universes that predate our own. Or it could engineer self-improving space probes that adapt their missions in real time, chasing anomalies beyond human programming. Some theorists even suggest that artificial intelligence, unshackled from biological limits, could one day formulate questions we haven't thought to ask, like a child teaching its parent a new language. So while AI won't replace astronomers, it's already redefining what's possible. In the hunt for dark energy, extraterrestrial life, or the true nature of time itself, silicon mines might just be the partners we need to translate the universe's whispers into a language we can finally understand. The next cosmic revelation could emerge not from a telescope's lens, but from the silent hum of a neural network connecting dots across the void. Think you need a PhD or $1 million telescope to explore the cosmos? Think again. Some of astronomy's biggest breakthroughs have come from everyday people, teachers, students, even retirees poring over data in their living rooms. This is the magic of citizen science, where curiosity matters more than credentials, and the universe becomes a playground for anyone with an internet connection. Take the Asteroid Hunters project, where volunteers sift through telescope images to spot space rocks that might have slipped past automated systems. In 2020, a German high school teacher discovered a near-Earth asteroid now officially named 2020 G1, proof that you don't need NASA clearance to make your mark in the solar system. Or consider Galaxy Zoo, which lets participants classify galaxies by shape. When Dutch schoolteacher Hanny van Arkel stumbled on a strange green blob in one image, astronomers were stumped. That blob turned out to be a never-before-seen phenomenon, a quasar-lit gas cloud now called Hanny's voorwerp, Dutch for Hanny's object. It's still studied today as a clue to how galaxies evolve. But the opportunities go far beyond spotting celestial oddities. Projects like Planet Hunters TESS invite you to analyze light curves from NASA's Exoplanet Hunting Telescope, searching for the telltale dips caused by distant worlds. Over 500,000 volunteers have joined the hunt, leading to discoveries like the 8-planet system Kepler-90, a solar system rivaling our own in complexity. Then there's backyard worlds, where you can scour infrared maps for brown dwarfs, failed stars lurking in our cosmic backyard. One participant, a retired police officer, found a previously unknown binary brown dwarf system just 30 light-years away. The tools are simpler than you'd imagine. Many projects use platforms like Zooniverse, designed for beginners with no prior training. You might track solar storms with NASA's Sungrazer project, or map lunar craters with moon mappers. Some initiatives even gamify the process. In EVE Online's Project Discovery, players analyze real telescope data while earning in-game rewards. What makes this so revolutionary isn't just the discoveries, it's the democratization of science itself. When a teenager in Mumbai can flag a supernova, or a baker in Toronto helps identify a pulsar, it reshapes who gets to participate in humanity's oldest quest, understanding the stars. And with projects now expanding into AI-assisted cosmic archaeology, like reconstructing the Milky Way's history through stellar motions, the frontier keeps widening. So grab your laptop or smartphone. The next cosmic revelation might not come from a mountaintop observatory, but from your couch. After all, the universe doesn't care who's looking, only that someone is. And that someone